Good morning. We will start this Wednesday morning session with part 2 of Laurentius' mini course on Alexander polynomials. And well, again, I think the first session was a wonderful mini course, and it is also important that we interrupt, we ask questions to make this also as helpful as possible. So
Thank you. Thanks for showing up for the second part. It means you did your homework. So I will, maybe I should recap what I did last time. So I ran through a quick overview of some stories about quasi-projective or Kähler groups, giving you examples and some homework. And then I said I'm gonna focus on fundamental groups of plane curve complements. And since I'm slightly incompetent in computations of such fundamental groups, I prefer to just talk about invariants of those fundamental groups, which amount to studying various distinguished covering spaces of the complements. So the first such invariant was the classical Alexander polynomial, which was defined by Anatoly Lipgover by using the same techniques as in classical knot and link theory. And let me just remind you the notations. So I have a plane curve C in C2, which is defined by a polynomial of two variables, little f. I didn't write the polynomial here, but I can also regard this complement as sitting in the projective plane, from which I throw out the projectivization of C and the line at infinity. For convenience, I will assume the line at infinity is transversal to the projective curve, but this is not necessary always. I'll make a distinction along the way. And then the first cover that one can look at in this case is the one induced by the defining polynomial f itself. So if I restrict the polynomial f to the complement of the curve, so the polynomial f defines the curve, on the complement it gives me a map to C star. I take the induced homomorphism on fundamental groups, and the kernel of this homomorphism defines a z-fold cover called MC here of the complement, and you can think of this as being the pullback to M of the universal cover of C star. So F is a map from M to C star. Over C star I have this exponential map, this universal cover. I pull it back over M under F. What we get is a space, a covering space MC, which has the integers as a deck group. So this deck group is going to act on the homology of the covering, and as such the homology of the covering becomes a module over the group ring of the deck group of the integers, which can be identified with Laurent polynomials in one variable. Anatoly Lipgover in the early 80s showed that the first homology group of this cover, which is the analog of the Alexander module in knot theory, is a torsion module over this Laurent polynomial ring, even without the assumption of transversality at infinity. I listed again here the transversality at infinity because the result was reproved later on by several people under this assumption, and there is a nice connection to the Milnor fiber of the homogenization of F, which I'm going to discuss on the next slide. So let me just recall the definition of the order or the Alexander polynomial of the curve or of the fundamental group. So this is essentially the characteristic polynomial of the T action on this Alexander module. All right, so now I'm going to maybe state a few results about the Alexander polynomial, which can be seen as rigidity properties on the fundamental group, and as such they impose various obstructions on the fundamental group. Okay, before I do that, maybe let's make the connection to the Milnor fiber precise. So I said the projectivization of the curve, the C bar in CP2, is defined by a degree D homogeneous polynomial, which I call capital F. And it has, as any homogeneous polynomial, it has the Milnor fiber, the fiber of this homogeneous polynomial over 1. And this is the fiber of the Milnor fibration. So the Milnor fibration is a map to C star, circling the base C star once leads to a monodromy homeomorphism of the fiber. So this is a classical object that you already saw in several talks, especially for germs of singularities. So germs of singularities, hypersurface singularities, have attached Milnor fibrations to them and the corresponding monodromy homeomorphism. This is the, so to speak, global picture where you work with a homogeneous polynomial, in which case the fibration is actually global. All right, so in this case the monodromy is actually quite simple. It's just the multiplication by a primitive d-th root of unity, d being the degree of the defining polynomial for the projective curve. And this cover, this Milnor fiber can be seen as the default cover of the projective complement. So I keep switching between the projective complement and the affine complement. Both of them are useful for trying to understand the Milnor fiber, which is actually the main object in singularity theory that we don't know much about. You saw, for example, Pablo's talk yesterday. I mean, it's still a lot of work, heavy work done in this direction. And here I'm just trying to understand, for example, the first Betti number of the Milnor fiber, which is already a big deal, right? All right, so under the transversality at infinity assumption, Dig Randall showed that the Alexander polynomial of the curve, of the affine curve, equals the characteristic polynomial of this monodromy of the Milnor fibration for the homogenization of the defining polynomial. And this has very nice consequences, which I'll list here. So first, the degree of the Alexander polynomial is the first Betti number of the Milnor fiber. If the curve is irreducible, triviality of the Alexander polynomial is equivalent to the fact that the first homology of the Milnor fiber is at most a finite group, right? So just Betti number is trivial. If the fundamental group of the projective complement is a finite group, well, then that's also true for that, the fundamental group of the Milnor fiber, which is a covering of the projective complement. So if the fundamental group of the Milnor fiber is a finite group, then the homology is the same, at most a finite group. So the Alexander polynomial is trivial. Another nice result using this covering given by the Milnor fiber for the projective complement is that, of course, in principle, you can think of this Alexander, so this Alexander polynomial is a polynomial in the variable t, and you may wonder what is, does the root 1 appear there in the Alexander polynomial? This corresponds to the eigenvalue 1 for the monodromy homeomorphism up there in Randall's result. And this can be computed effectively as the number of, so the multiplicity of this factor t minus 1 in the Alexander polynomial or in the characteristic polynomial of the Milnor fiber is simply the rank of the unipotent part of the homology of the Milnor fiber, which is known to be just the number of irreducible components of the curve, minus 1. Okay? Anatoly Lipgober proved this result that shows that the Alexander polynomial divides a very specific polynomial depending only on the degree of the curve. And this also follows from this characterization of of the relation to the Miller fiber. And at all this result, use the link at infinity, this Hopf link on D components, and the corresponding divisibility result. I'll get back to that in a minute. But this already has very nice consequences. This kind of result here says that the Alexander polynomial is a product of cyclotomic polynomials. And, well, also from the divisibility, we can say not only that the roots of the Alexander polynomial are roots of unity, but also that they are d roots of unity. And this is where this transversality to the line at infinity is important, of course. Otherwise, you just have some cyclotomic polynomials. Okay, so this is something about the fundamental group of the curve, right? Because you can think of the Alexander polynomial as being associated with the fundamental group of the curve, of the affine curve complement. And now I'm telling you that this Alexander polynomial has only d roots of unity, or it's cyclotomic or something like this. And now you can think, I don't know, take the fundamental group of a knot complement or of a link complement and calculate its Alexander polynomial any way you know. And, well, if you get something odd, maybe figure 8 is something that comes to mind, right? Then that fundamental group cannot be of this sort, of the plane curve complement situation. All right. Yeah, actually, I put this here. Sorry, I shouldn't drink too much at night. It affects memory. All right, so we already see some of the first abstractions here on fundamental groups of plane curve complements derived from properties of the Alexander polynomial. And this is actually, I wrote down the Alexander polynomial for the figure 8 knot. It's clearly not cyclotomic. All right, but on the other hand, many of the classical groups can be realized as fundamental groups of plane curve complements. And I will actually write down the examples for the braid groups and groups of torus knots. Okay, so we already saw this example before for groups of torus knots. So I take Oka's curve, which was this projective curve using powers of P and Q being co-prime integers. And then I throw out a general line at infinity. The fundamental group for the affine curve turns out to be that of the torus knot of type PQ. This is what Oka's point was in constructing this curve. And as such, the Alexander polynomial is also known. So it's just this very symmetric looking thing that I wrote down there. For torus knots, for braid groups, this is a bit more complicated. I'll say it later on. But you also saw some reference to some braid groups early on. I mean, if you remember anything from Monday, I don't. So let's see. I actually am trying to guess what's on the next slide, but it doesn't strike a chord, so I have to click on it. Yes, relation to Miller fiber continued. This surprises me. All right, so I want to continue this nice interplay between Alexander polynomials of plane curve complements and the Miller fiber of the polynomial defining the projective curve. So again, take the Miller fiber for this homogeneous polynomial defining C bar. And recall that one of the consequences of this identification of Randel was that the degree of the Alexander polynomial is the first Betti number of the Miller fiber. Now, using the monodromy action, you can decompose the homology of the Miller fiber into a unipotent part and non-unipotent part. And this unipotent part was responsible for the power of t minus 1 in the Alexander polynomial. So you have a default cover of the projective complement, take the invariant part of this monodromy action of this H homeomorphism, and you get just the homology of the complement downstairs. And the rank is again R minus 1. So we saw this calculation done already several times yesterday for line arrangements. Is exactly the same calculation. But on the other hand, if you want to understand the first Betti number for the Milnor fiber, I have to figure out also the non-unipotent part. And this is something that came from Zariski, and it was continued by Eno, and actually Enrique wrote a very nice paper, and Anatoly, yes. So there is a way by you take a branch cover of CP2 along this projective curve, and using various Alexander dualities, you can identify this non-unipotent part from the Milnor fiber with the third Betti number of this surface. This is a surface in CP3 which has only isolated singularities. So you may think, well, I know how to calculate Betti numbers of surfaces, don't I? Well, it turns out we don't. This is a shame, but this is the status of singularity theory. So we don't know how to calculate very simple things. But this says that, well, if you try to understand Milnor fibers, you maybe should first understand simplest hypersurfaces with isolated singularities, their topology. So some people refer to this non-unipotent part as the jump in the Milnor fiber, because this unipotent part is always there, and this jump, I mean, may be 0 or not, right? This was, maybe I will, let me first state the problem. So the problem, one of the problems would be to calculate the fundamental group of the Milnor fiber. And as I said, the main difficulty is that this Betti number, just like the third Betti number of this branch cover of CP2, depends on the position of singularities of the projective curve. So this is something that Zariski already noticed, right? So this was his point, and the conjecture, for example, there is a nice conjecture in the case of line arrangements that I'm sure everybody in their youth tried and then maybe gave up. Some people are still trying. It says that if we actually have, if this homogeneous polynomial f defines a line arrangement in CP2, so it can be factored as linear factors, then the first Betti number for the Milnor fiber and the monodromy are combinatorially determined. So they are determined by the lattice poset of the arrangement. And there is progress in this direction, so there is some hope for line arrangements with double and triple points, for example. So, well, Alex Suciu and his collaborators, Dimka and Papadima, made some progress, and Anatoly Lipgober also, and others. But it seems that, I mean, double and triple points, I see this as the analog of nodes and cusps somehow, but but beyond that, things seem to be quite difficult. All right, so let me get to some of the more classical results about Alexander polynomials. So this is a relation of local and global topology, or local and global singularities. So each singular point on the curve has similar objects attached to it. So there is a local Milnor fibration, there is a local Alexander polynomial. So these things are just, maybe let me just state this quickly here, because this is something that we already saw. So each point has a link obtained by intersecting a small sphere in the ambient space with the curve, and a local link complement. In the tree-sphere, there is a local Milnor fibration over the circle. The Milnor fiber is just a bouquet of circles, their number being the Milnor number. And there is a corresponding monodromy homeomorphism for the local Milnor fiber, and the characteristic polynomial of that, which is called the local Alexander polynomial. So now the question was, well, what's the relation between what I defined earlier, the global Alexander polynomial, and these local Alexander polynomials? Maybe I should say one more thing here. So these local Alexander polynomials have a very nice feature, which already was mentioned earlier. Their zeros are roots of unity. So this is the nice monodromy theorem. Okay. So now Anatoly, I guess this was the first paper, right, in Duke in '82, showed that this global Alexander polynomial divides, well, besides this power of t minus 1, which is dictated by the number of irreducible components of the curve, divides the product of the local Alexander polynomials. This is actually, I mean, to prove this, one can, for example, use this boundary manifold that popped up in Vincent's talk yesterday. Was it Vincent? Was and I and others, I guess, refine this a little bit by reducing by restricting the attention along one irreducible component at a time. So this has some benefits in the long run, but the proof is very similar. There is no. Okay, now you can derive this cyclotomicity of the Alexander polynomial also from this fact, though I mentioned it earlier for it's coming from this Hopf link at infinity. So since local Alexander polynomials have only roots of unity, then this, by the divisibility result, the global Alexander polynomial will only have roots of unity. And here is a nice corollary that was perhaps one of the, when I saw this statement in the beginning, it kind of puzzled me a lot because I didn't have any content. I didn't know anything about Alexander polynomial, but it sounded cool. Look, I can actually tell by looking at the curve if it has only nodes and cusps, and the degree has some numerical property. I can tell if the Alexander polynomial is, when the Alexander polynomial is trivial. And this is one instance which is follows quickly from this divisibility results. If we have only nodes and cusps, nodes have Alexander polynomials t minus 1. Locally, cusps have t squared minus t plus 1. And, well, plug in the divisibility result there. If the degree is not divisible by 6, then there cannot be any global root of the Alexander polynomial. Because this should be roots of unity for the 6, right? I mean, sorry. The global roots of the Alexander polynomial should be roots of unity for the D, right? But the local ones are the eigenvalue 1 or roots of unity of whatever this t squared minus t plus 1 is. What is it? 3, 6, 6. Okay, so now let me mention another more recent work in this direction, which generalizes this picture to the quasi-projective case, and I find this quite interesting. So if you have a quasi-projective group, not necessarily the fundamental group of plane curve complement, and you take some epimorphism to the integers, and you take the corresponding covering, and the now the Alexander polynomial is defined by looking only at the torsion part of the homology of the infinite cyclic cover. So if you don't torque in the case of plane curve complements, it may happen that this first homology of the infinite cyclic cover has a free part also. But throw that away, only look at the torsion part, and we can associate an Alexander polynomial to that torsion part by taking the characteristic polynomial of the T action. And it turns out that this corresponding Alexander polynomial is a product of cyclotomic polynomials, just like in the case of plane curves. So this will tell us that those odd figure 8 knots or things like this, their fundamental groups cannot be, they're not quasi-projective, period, not just, they're not of the form pi1 of C2 minus a curve. So this was done by, I like to mention this because Liu was my student, so he he did this after he left me. He kept the best for the last. So, and he was Nero's postdoc at the time. All right. Now, what comes out from this divisibility result is again an enhancement of Zariski's philosophy that the local type of singularities affects the topology of the curve. And as I already mentioned last time, actually Zariski showed that position has an effect. The way this singularity sit in the ambient space, this also has an effect. Unfortunately for us, right? But fortunately for mathematics, has an effect on the topology of the curve. And this is also reflected in the Alexander polynomial, which again is much easier to calculate, and this is what Anatoly noticed. And the examples of Zariski can be now, we can look at it again from the point of view of the Alexander polynomial, and perhaps, well, let me mention the whole picture here, both fundamental groups and the Alexander polynomial, just to see the difference in complexity. So this sextics with 6 cusps, these are the things that Zariski considered, and by throwing out this generic curve at infinity, we get something in the affine space for which we can calculate the Alexander polynomials. And these are the two situations. The non-generic one was if the 6 cusps are on a conic, and then it turns out that the fundamental group is isomorphic to that of the trefoil knot complement. I will get back to this in a minute. These are torus knots, of course, the 2-3 torus knot. And the Alexander polynomial is, well, this is computed from knot theory. This is t squared minus t plus 1. But in fact, Zariski calculated the fundamental group as being the free product of Z2 and Z3. So these are special cases of Okas curves for the PQ being 2 and 3. And then the general situation is if the 6 cusps are not on a conic, and in that case it turns out that these fundamental groups, the fundamental group of the complement is abelian, so the Alexander polynomial is trivial, and Zariski already knew what the fundamental group is. It's the product of Z2 and Z3. So the fact that the fundamental group in one instance is abelian and in the other one is not already distinguishes these two types of sextics. But of course, the Alexander polynomial is much easier to handle, and that already says that these two types of curves are different. Okay. Are there any questions? Sorry, I have a feeling that I speak too fast. All right, so let's move on with, I promised I'll write down the, well, at least I'll say something how the Artin's braid groups can be realized as fundamental groups of plane curve complements. So this is, as I know, the construction was due to Moishezon. So I wrote there the presentation for the for this Artin group on braid group on K strands. And how does this appear as fundamental group of a plane curve in C2? Well, the projective completion of this curve is the branching locus of a generic projection to P2 of a degree K smooth surface. So if you didn't see this construction before, it may not necessarily ring a bell, but this is a classical construction nowadays. And in fact, the curve you obtain in this case, this branching locus, is quite nice. It has only nodes and cusps. The degree is K times K minus 1. You know exactly how many nodes and how many cusps are out there. And we already saw this. If K is 3, this is exactly the 6 cuspidal sextic with all cusps on a conic. And this B3 is what already popped up earlier in Zariski's example. this pi1 of the trefoil knot. So we know it's Alexander polynomial, right? But we can actually calculate the Alexander polynomials for all. Yeah, go ahead. Is that the one with no 9 cusps? Yeah. Do you mean this Arnold description? Is it the same curve?
Some embedding.
It is actually great to see the legends arguing.
Embedding C2 into complement discrete. No, this is truly new theorem. It was breakthrough.
I think Anatoly is also. Moishezon was your advisor? Right, so he has a right to defend this construction. All right, so let me just conclude this example by saying that one can actually calculate all the Alexander polynomials. It's not too complicated. So using, for example, Reidemeister-Schreier to get presentations for commutators. And all break groups from 5 strands and more, you have trivial Alexander polynomials. We saw that P3 has Alexander polynomials t squared minus t plus 1, and then one can calculate, just a sec, one can calculate again by, this is a little bit more calculation, you can calculate the one for the 4 strands. Yes, go ahead.
So I have a question. For k equals 3, you say that the cusps are on a conic. For
Yes.
bigger k, do you also have properties like this, that the singular points are on special smaller degrees curves?
Not that I know of.
No? Okay, thank you.
Yeah, so this quartic case is the special one here, at least in my opinion, because I had to work a bit harder to calculate, for example, the commutator, presentation for the commutator. But yeah, from 5 up, I think everything is as generic as it gets, right? All right. Good. So now, since we're still on the Alexander polynomials, there are various algebraic geometric descriptions of it, and I listed here the names of some people who have obtained such descriptions by various approaches. Anatoly, Lozier, Vacquier, Henault, Artal, Bartolo, of course. But let me also mention here a very interesting thing that appeared more recently in a paper of Jose Ignacio Cocoludo and Anatoly. Is this kind of interplay between, if you like, topology or algebraic geometry and number theory. So they related the degree of the Alexander polynomial for curves with only nodes and cusps to ranks of Mordell-Weil groups, and that, well, they managed to get this kind of universal bound for the Alexander polynomial, which is a linear bound, right? Of course, you do have a bound coming from those divisibility results with the link at infinity, but this is a linear one. And they also have a very nice example where, so divisibility results for such a curve would tell you that the Alexander polynomial, this is irreducible. There are no powers of t minus 1 in the Alexander polynomial. So you only get powers of t squared minus t plus 1, that being the Alexander polynomial of a cusp. But then it's like, the question is, what is the highest power you can have there? And there are known examples up to power 3, and they came up with an example of where power 4 shows up. So it's a very nice paper in Krell, not long ago, as I remember, right? All right. This is something I always liked, and I want to emphasize it here, even though I don't go into details. You can now put additional structures on these Alexander modules, right? You can do topology, that's fine, but you can do a little bit more. And these are finite dimensional vector spaces, these Alexander modules. I work with rational coefficients now. And, well, you may wonder, do these things have Hodge theory on them? And Anatoly, and then I think there is another paper by Kulikov, so these are two people, not the same one, show that these Alexander modules also carry canonical mix of structures. So besides being a vector space, they have this Hodge and weight filtration on them. And Anatoly generalized this to higher dimensional hypersurfaces with only isolated singularities. And later on in my, well, coming out of my thesis, but also Anatoly and Dimka generalized this further to arbitrary singularities on hypersurfaces in general position at infinity. So this general position at infinity is still useful for various purposes, again, in relation to the what is called Alexander polynomials at infinity. All right, so now more recently, of course, this problem was in the back of my mind, and I always wanted to see how far one can go with the construction of mixed structures on Alexander modules of quasi-projective manifolds in general. And I had some chats with Stefan Papadima, the institute in Bucharest, who claim that doesn't matter what quasi-projective manifold you have, the Alexander modules defined by an algebraic, by a map, right, to a circle, should have a canonical mix of structure on them. And I had some fantastic students here, and Eva is one of them, and Moises is another one, and Christian Geske, and of course Botong Wang. He's not my student, he was postdoc at the time. We managed to construct a very general mix of structure on the torsion part of the Alexander modules. In the case when these Alexander modules are induced, just like in the case of a plane curve, by an algebraic map to C star. This is a paper that's still waiting to be published, so it's hot. Okay. Well, I praised a lot the Alexander polynomials, but like any good thing, there are some downsides. And according to Mutsuoka, there is a weakness of Alexander polynomials. And this was reflected in this calculation of that he did with Sakamoto. I'll mention now here the statement. So assume that we have two projective curves intersecting transversally and take their union to be this projective curve in P2, this C bar. Consider again a generic line at infinity with respect to all these curves and take their affine pieces. And then Oka Sakamoto showed that there is an isomorphism induced by inclusions from the fundamental group of this C, which contains both C1 and C2, and the product of the complements of each one curve at a time. But on the other hand, one can calculate, it's not hard to see that this transversality kind of kills all the interesting things in the Alexander polynomial, and the only thing you get is this power of t minus 1, which is dictated by the number of irreducible components of the curve. So Mutsuoka's philosophy here, I read this from one of his surveys, so I assume everybody has its own or their own interpretation of this fact. But he said this Alexander polynomial is weak because look, the fundamental group sees the components of the curve, but the Alexander polynomial does not. So then what do you do? So there are many ways to move away from the classical Alexander polynomial, and I'm going to mention a few here, but you can twist the Alexander polynomials by representations of the fundamental group, or you can start considering higher and higher coverings of the complement, for example, the universal abelian cover or various solvable covers. Now, this universal abelian cover leads to this what's called Alexander or Alexander and or character varieties, depending on who you talk to about these things. The terminology is not very consistent. And there are many, many results in that direction. This is related to this jumping loci that I mentioned earlier for quasi-projective groups, and Anatoly and Alex Suciu and his collaborators, and also myself and Dimka and so on, and especially the Saragossa group. There are lots of results in this direction. There are too many to put on slides, so I decided not to mention it. But I should say something about the twisted situation because it's also very much related to what I just said, and it's actually very similar. So this twisted Alexander invariants were introduced in the not theoretic context by Lin, Wada, Kirk, and Livingston in the 90s, and then they were used for 3 manifolds, for real closed 3 manifolds by Friedel, Vidusi, and they actually have very nice applications. For example, you can detect symplectic existence of symplectic structures on a 3 manifold cross a circle, this kind of things. You can detect fiberness, right? And then Cogoludo and Florence have a very nice little paper where they actually adapted this twisting to the study of plane curve complement. And the nice thing is that they found examples, new examples of, at least that's my recollection. I wrote these slides. I didn't recheck this, but my recollection is that there is an example of a Zariski pair that cannot be detected by the classical Alexander polynomial, but the twisted Alexander polynomial shows that this is indeed a Zariski pair. So let me oversimplify the definition here for you. I want to keep things as simple as possible. Let's start with the path-connected CW complex with fundamental group pi. Later on, this will be a plane curve complement. Let's take an epimorphism, even I said homomorph, let's say an epimorphism to the integers. We already saw one of those, induced, for example, from the defining polynomial of a plane curve. And then take the z-fold cover induced by the kernel of this epimorphism, and let's call that kernel pi bar. Now, so up to now, everything was as before. But now let's bring in some representations. So let's take a finite dimensional vector space, C vector space, or you can take other fields that are invariant under conjugation. Let's say of dimension L. And take a representation of the assume this is a representation of the fundamental group. Denote this representation, V with the representation by V rho. And now what I'm gonna do, so before I go through this, earlier when we looked at the classical Alexander polynomial, we looked at the homology of this z-fold cover. So we look at the homology of the chain complex of the z-fold cover. Now I'm gonna twist that chain complex of the z-fold cover by the representation of the fundamental group rho, or better said, the induced representation on this kernel of the epimorphism to the integers. So here, down here, this pi bar, so pi bar was this kernel of the epimorphism epsilon, And this, of course, acts on the covering, but it also acts by restriction of the initial pi action on V. So we get a twisted chain complex whose homology we denoted by, or it's classically denoted by the homology of the Z-fold cover with coefficients in this local system, V rho. And this is what is usually called the twisted Alexander module of, now we have all this information to carry around, so the space M, the epimorphism to the integers, and the representation. Okay, and as we'll see, these things are not much different at the philosophical level than the classical invariants, but on the other hand, as I already mentioned, they are more powerful for detecting Zariski pairs, for example. So let me get back to our setup of plane curve complements. So this is a little thing that I think it was already known from Cogoludo and Florence. I don't remember this, but our calculation was slightly different using this link at infinity. So no matter what choices of an epimorphism and to the integers and representation you make, this twisted Alexander, the twisted Alexander modules are torsion. You only care about the first one, right? The zeroth one is always. It's a torsion module over Laurent polynomials again. So maybe I should say, so here, of course, you still have a T action, right? So these are, if I manage to show these things are torsion, they have associated Alexander polynomials to them. In general, what you do is you take the torsion part, and that's the benefit of working over a PID, right? You can take the torsion submodule and then associate an order to that. All right, so these Alexander modules, even in the twisted case, are torsion. And if you restrict now to the classical case of this linking number or whatever I called it, I redid the slides, but I didn't do this. I didn't change this. So this epsilon was induced by the defining equation of F. And then take the trivial representation, then you get back the classical Alexander module. So the result I mentioned up here reproves in this case with the transversality at infinity this result of Anatoly about the torsion, but it's essentially the same proof, right? So you have to track a little bit the induced representations, but that's not too hard to do. All right, so we have a twisted Alexander polynomial of the curve. Call it delta C, epsilon rho, and this behaves pretty much like, and this was studied, as I said already, in this paper by Florence and Cogoludo. It behaves very much like the classical one. So let me maybe state something that was maybe not known. Where do the roots of this twisted Alexander polynomial lie? And this is something that Anatoly also worked out in some special case, even for more general complements. So let gamma infinity be the meridian about this line at infinity in the fundamental group of M. So the representation is going to take this gamma infinity to some matrix, to some automorphism of V. And I'm looking at the eigenvalues of the inverse of that matrix, so just the inverses of the eigenvalues. But possibly, these eigenvalues don't have to be distinct. So L was the dimension of V, right? So this is, I go all the way to a dimension. Then the roots of the twisted Alexander polynomials end up to be contained in the splitting field of this polynomial here over the rationals, which is cyclotomic over the rationals to which you add these eigenvalues of what's called a representation at infinity. So for the trivial representation, I put this here because this is the generalization of Anatoly's result that the Alexander polynomial divides this thing depending only on the degree. So for the trivial representation, of course, you get just t to the d minus 1 here, and this just says that the roots of the classical Alexander polynomials are roots of unity of order d, which we already knew. But this is the right way to generalize this statement. This is perhaps the most technical slide in my talk because it has too many notations. All right, so you can do you can have run through divisibility arguments just like you do in the classical case. So again, you have this local complements, you have local fundamental groups, you have local representations and local epimorphism induced via the local inclusions of these complements into the global complement. So there is an induced map of fundamental groups, and just restrict the representations, compose the representation rho and this epimorphism with this induced map, and you get we get some corresponding objects locally. So you have local twisted Alexander modules, and this is a little observation that we made, that all these things are also torsion. So this is not a priori clear. It's not like the classical situation where just the Milnor fiber does the job for you and there is nothing else you can do. In this case, the representation in principle could make these local polynomials interesting, but in the end still the Milnor fibers govern everything. So these are torsion, and now you can define local Alexander polynomials and you can ask the same question: how are these things related to the global ones? And I'm not going to state it here, but there are statements already in Cogoludo, Florence, and we did this. By the way, Wong was another student of mine. This was part of his thesis. And these divisibility results again relay local and global polynomials, and you get this kind of numerical consequences like I mentioned earlier with the roots. The roots are dictated by the local roots. All right, I will not emphasize this because I was told to speed up a little bit. Sorry, I think I speak faster because I'm under pressure. The boss told me to speed up, so. All right, so let me move to some other sort of invariants. So Alexander type invariants, more or less you see everywhere in this conference because they come up in the disguise of the Milnor fiber and the monodromy. But there are other sorts of invariants that can that are defined for arbitrary CW complexes, which can be adapted to this setup of plane curve complements. And rigidity properties for this kind of invariants again reflect on the fundamental groups. Every single invariant I'm gonna discuss, just as before, comes from looking at some distinguished covering space of the complement, of the curve complement, or in fact of any topological space. So let's take again a topological space, which is a finite CW complex, and let pi be the fundamental group. And now let's fix a cohomology class of degree 1 with real coefficients. So this corresponds to a homomorphism now from the fundamental group to the reals. Not to the integers, but to the reals. Take the image of this homomorphism, and let's call it gamma C. So this is a subgroup of R. It's a discrete subgroup. It looks like Z to some rank. So that rank is called the rank of the one form I started with. And this induces a homomorphism from the fundamental group pi to this Z to ds. So this is very similar to what one does with multivariable Alexander type invariants. So take the covering of M corresponding to the kernel of this Xi. So now we get a finitely generated Z, well, it's a finitely generated module over the group ring of this gamma Xi group. So this gamma Xi again is Z to some power to the rank. So this is, you can think of this as Laurent polynomials in a bunch of variables. Okay, it's just some distinguished cover. What do we do with it? Well, taking the rank of this corresponding homology of the cover, maybe I should try to slow down a little bit. So what I'm doing here is I'm looking at the homology of this cover acted on by the deck group gamma xi. So I regard it as a module over the group ring of this gamma xi. And then I take the fraction field of this weird ring, and let's call it QXi. And I take the dimension over that fraction ring. So this is what is called the rank of this, I don't know, it's some sort of Alexander type invariant, but for a higher covering. There is a, of course, now I'm working over something that is not necessarily a PID. So if I want to play the game of Alexander polynomials or Alexander modules or things like this, it makes sense to try to find a better localization of the fundament of this ring that will be a PID. So this is what's called a rational Novikov ring. I'm not really gonna define this. It's just local, a different sort of localization. But these Betti numbers, Novikov Betti numbers, can be seen also as the ranks over this PID. So, yes. For the Betti numbers, there is no difference. Yeah. So this will become clear in the next slide. All right. So then there are other sort of invariants one can talk about called Novikov torsion numbers. So these are essentially defined by looking now the torsion part. This is the benefit of working over this PID. You look at the torsion submodule of this Novikov module, so to speak, and look at the minimal number of generators. These are called the Novikov torsion numbers. So I have a bunch of numbers that look like essentially the degrees of Alexander polynomials earlier. So these are the analogs of the first Betti number of the Milnor fiber, but now it's some weird twisting. It's easier to just focus on properties. So these Betti numbers, they are called Betti for a reason because they also calculate the Euler characteristic. It's just like it happens, right? You start with a space, finite dimensional CW complex, and you calculate its Euler characteristic through the Betti numbers. But then you take some covering, possibly infinite covering, and you look at, you cannot calculate the Euler characteristic in terms of the Betti numbers of that covering because the covering may be infinite. But if you regard that covering as a module over the Deck group acting under the Deck group action, then it is possible to assign finite numbers typically to it, and those like of this sort, and those numbers calculate also the Euler characteristic. Like the ranks of the Alexander modules, right? The ranks of the Alexander modules as Laurent over Laurent polynomials will also calculate the Euler characteristic. All right, so these Betti numbers, so this is essentially what the definition comes to. So they are all bounded above by the one corresponding to the trivial homology class. Well, the one corresponding to the trivial homology class is just the usual Betti number. So these are all this for any Xi, for any first homology class, these are all bounded above by the, so there is a sort of monotonicity. Okay, so what to do with these numbers in the case of plane curve complements? So let me briefly state this. I'm gonna select a distinguished class of cohomology classes of degree 1, the so-called positive ones. So these are the ones that take positive values on all these meridians around the irreducible components of the curve. And a later result that I proved a while back with Stefan Friedel says that for such choices, for positive cohomology classes of degree 1, you get essentially the corresponding statement for the torsionness of the Alexander module. So if you look at the classical Alexander modules of the complement, the zeros in the first one are torsion, so the ranks of Laurent polynomials are 0, and the one in the middle is free of rank equal exactly to the Euler characteristic. So these are reflections of that fact. So there are no, I mean, the ranks of the Alexander modules are all trivial except the one in the middle, which is calculated by the Euler characteristic. And the torsion ones are always 0 in this case. So this kind of vanishing properties are again dictated by something I'll mention at the end. So I want to keep the upshot at the end, but I already kind of hinted at using this link at infinity. So this link at infinity is a very nice object which is fibered and so on, and it kind of gives you vanishing of all these objects. All right, so you can play this game with, let's twist the definition I gave you earlier by some representation of the fundamental group. I'm not going to do this, but
Can I ask you a quick question?
yes.
Is this something special about curves, or does this work for hypersurfaces?
This is true for hypersurfaces, right? But I wanted to, since I relate only to somehow to invariance of the fundamental group, I wanted to reduce to curves. But our result is indeed true for any hypersurfaces in general position at infinity. Right, this is, yeah. And of course there are, maybe I'll not get into this, but there are nice relations to what's called BNSR invariance that Alex Dimka and, Alex Suciu and his collaborators worked on. And this was in fact the motivation for such calculations. Okay. So let's move to the final part. So for the next hour, I'll talk about L2 Betti numbers. So these L2 Betti numbers, they came up, they were introduced by Atiyah and then used by many people, but in particular by Zinger to reformulate this Hopf conjecture I mentioned in the beginning about the Euler characteristic of a spherical Keller, or a spherical, for that matter, real manifolds. And that conjecture was reformulated in terms of vanishing of certain higher up invariants, which are exactly these L2 Betti numbers. So I think this, I'm not sure I say the history right, but I think the story was that people are looking to assign some sort of Betti numbers to covering spaces, but as I said, these covering spaces, for example, the universal covering is infinite. So what sort of Betti numbers are you gonna attach? Well, a good idea is to look at the homologies of covering. It says modules over the deck group action, for the deck group action. But the problem is that these group rings of the deck groups are not necessarily Noetherian, so they may not have good dimension theory attached to them. So then various completions of such group rings came about, and some of them have good dimension theories, and this is how L2 Betti numbers are introduced. So I'll just state briefly the principle without necessarily giving you the details of the construction, but it's a quite useful invariant. So you can attach L2 Betti numbers to any CW complex with a countable group, gamma attached to it, and the homomorphism from the fundamental group of that complex, of that CW complex to gamma. You can think of this gamma as being, I don't know, the group itself, the fundamental group itself, right? And then how are these L2 Betti numbers defined? Well, you take again the distinguished cover of this M given by the homomorphism alpha. So the kernel of this homomorphism will give you a covering, M alpha. And you twist the chain complex of that covering now by some completion of this group ring of the D group of the covering, which is gamma in this case. But this completion is chosen so that you have a good dimension theory. It's defined in terms of L2 forms. And the downside of this construction is that this dimension could be infinite. So these are some infinite dimensional traces. You may end up with some infinite thing here for this L2 Betti number, in which case it may not be very useful for our purposes, but we'll see the fundamental groups we're looking at have finiteness properties, and that's exactly the special situation. So this completion is called the von Neumann algebra. There are various constructions of it. I actually, if you haven't seen this, I recommend Luke's book on L2 invariants. It's like Wolfgang Luke. There are various incarnations of L2 invariants defined algebraically, through differential geometry to analysis, and this book puts them nicely together. These are homotopy invariants of the pair I started with, this CW complex M and the homomorphism alpha. They also calculate the Euler characteristic, so the same principle applies, right? You regard the covering under the D group action as an equivariant object, and if you choose the right completion of the group ring of the D group, then you should be able to do dimension theory. And just a remark here, there is a reason why I put Novikov before L2, because these Novikov Betti numbers are special cases of L2 numbers, but not, at least I don't know if distortion Novikov numbers have such an interpretation, or the twisted ones, right? So you just take, for this cohomology class Xi, you take the group gamma to be this image of Xi, so this Z to the rank. And the L2 Betti numbers for this homomorphism gives you exactly the Novikov Betti numbers. Well, this is easy to check, just go through the definitions. So L2 Betti numbers are more general. I should say there are other versions of invariants that I looked at, like was called higher order degrees. So this is something that Eva worked on also with Cocoludo. So these are invariants attached to some solvable covers of the space M, defined, associated to terms of the derived series of the fundamental group, or if you want to throw out the torsion, it's called rational derived series. And these are also special cases of L2 Betti numbers. So L2 Betti numbers are somehow like the more general, so it's like the lotus of Betti type invariants. All right, so back to curves. The same situation as before, affine curve in general position at infinity. I'm gonna call this homomorphism alpha I start with admissible if it factors through, if this homomorphism induced by the defining equation of F from the complement from pi 1 of M to pi 1 of C star factors through this gamma. So I want somehow this infinite cyclic cover, this Z-fold cover induced by F to be an intermediate cover in the tower that goes to this M alpha, to the cover defined by alpha. As you can guess, I mean, all these things have to do with, in the end, everything seems to be a twisted version of the Alexander module, but the twisting goes in various directions by various completions of the group ring. All right, so a little bit more setup for such an admissible homomorphism alpha. And as before, pi bar is the kernel of the homomorphism induced by the defining equation F. We have some corresponding objects, gamma bar. So gamma bar will be the image from, so I have an induced homomorphism from pi bar to this gamma, which is obtained by taking first the subgroup inclusion in the fundamental group and then applying this alpha. So I call this gamma bar, and there is an induced map alpha bar, of course, from, because this gamma bar is the image starting on pi bar. So there is an induced map, call it alpha bar, from the subgroup. So this subgroup is the fundamental group of the infinite cyclic cover of F. Sorry, I didn't do it. To gamma bar. Okay, so we can attach L2 Bethe numbers to these two situations, the complement and the given admissible homomorphism, but also the infinite cyclic cover and the induced homomorphism on its fundamental group. And at least for the second part here, since the infinite cyclic cover is infinite, I mean, there is a reason we call it infinite, a priori there is no reason for these L2 Bethe numbers of the infinite cyclic cover to be finite. Maybe I should say that there are still open conjectures about these L2 Bethe numbers, that they are rational and things like this, right? So these are conjectures from Atiyah which are still open. So let me write down some results about L2 Bethe numbers, and I promise I'll finish in 5 minutes. So for such an admissible homomorphism from the fundamental group to this countable group gamma, the L2 Bethe numbers of the complement itself, just like the Novikov Bethe numbers, they all vanish except in the middle degree. And again, this is true for hypersurfaces in general position at infinity with arbitrary singularities. But again, the definition for curves can be adapted just from the fundamental group. So that's why I state here things just for fundamental groups, for curves. Okay, as a corollary, the L2 Bethe numbers, of course, if you look at the definition, you don't really need this. This is a simple-minded thing. I put it here for the students if they are still awake. So of course, besides the vanishing, the other possible L2 Bethe number in this situation is just the Euler characteristic. And the Euler characteristic is very easy to calculate for plane curves. And this is the, this is the calculation. So it's just what you get in the smooth case, from which you throw out the contributions from the singularities, which are just the Miller numbers. All right, so this is for the complement itself, but then you may look at the infinite cyclic cover with its induced homomorphism alpha bar and look at the L2 Bethe number there, and it turns out that this is finite. And this is, again, not something that one would normally expect. And in the end, the philosophy of actually obtaining finiteness is very similar to all these things about Alexander modules. But in the case of plane curve complements, it's an obstruction on the fundamental group. An upper bound is determined by the local type of singularities. I wrote here everything that comes in, the Milnor numbers, the number of branches, the genus, and so on, the degree. Don't worry too much about it. The important thing here is that the L2 Bethe number of this infinite cyclic cover depends on the position of singularities. So these are still very fine invariants, unlike just the invariance of the complement itself. And this can be checked on the same example of Zariski. And initially I was very hopeful that I can detect new Zariski pairs, because I don't like fundamental groups very much. I'm sorry, this is about fundamental groups and I talk about fundamental groups, but as I said, I'm a bit incompetent at calculating fundamental groups. I hope that I can actually, come up with new Zariski pairs just by computing this kind of L2 Bethe numbers or Novikov Bethe numbers or this kind of things. And it was very encouraging to see that these invariants are indeed sensitive to the position of singularities, as they should, because in the end they are generalizations of the classical Alexander polynomial. But somehow, to my knowledge, to this day, there is no example of Zariski pairs that can be detected from the L2 Betti numbers and not from anything else. So this is still, I still ask any incoming student to keep this in the back of their mind, and maybe, who knows, maybe staring at the computer long enough, you come up with, I'm always amazed when people come up with these examples of, I don't know, 10 lines that do this and that, or this McLean arrangements or things like this, right? So I can't believe this is just divine inspiration. I mean, this is hard work. Okay, so quick consequences of finiteness. Of course, we do all this finiteness, all this rigidity, so that in the end you throw out some things, right? Say this group cannot be such and such. And these are things that, for example, relate to this finiteness of L2 Betti numbers. So if you take what's called complement of boundary links, for example. So these things have infinite L2 Betti numbers. So they cannot be of this sort that we're looking at, pi ones of plane curve complements. Well, here I related this thing with the central extension. So remember, this fundamental group of the projectivization complement sits in a central extension by Z of the affine group complement. Okay, some concluding remarks. All invariants of plane curve complements that I mentioned here are dominated by what's called the corresponding invariants of the link at infinity, and this was Anatoly's philosophy and our philosophy later on, and many people have done this, also Cogoludo, Florence. And so there are two things. Around the line at infinity, you have a little tubular neighborhood whose invariants dominate the ones we're considering here, but also the ones in a boundary neighborhood of the curve itself have their own invariants, this boundary manifold, which dominate the ones we're looking at. So studying those types of invariants for this three manifolds, so to speak, will give you upper bounds on the invariants I discussed here. And all these results, as Alex Suciu was. So yesterday he was asking which Alex. There is an Alex here and there is an Alex there, and perhaps there is an Alex somewhere else. Yeah, there and so on. It's a popular name. All these results extend to higher dimensions, arbitrary singularities, but typically one has to bring in a little bit more heavy machinery to do this. So of course I like perverse sheaves and intersection homology. So this is one way to proving this kind of results. I'm sure there are classical ways as well. And one can also prove similar statements by relaxing this transversality at infinity, this transversality of the hyperplane or line at infinity. For example, in the case of hypersurface complements, you may assume you have transversality except at finitely many points. And these results are still of the same nature. They are still true. And this appeared, for example, in Anatoly's work, and I did something with Eva for this higher order degrees. I think that's all I had to say. And I also did my homework. Last time I didn't have any pictures, drinking pictures, so this time I actually managed to gather some. All right, thank you.
Thank
Did
you.
I?
Yes.
I didn't.
You did a good job.
I did a good job.
You did a good job.
Time-wise.
Thank you. Time both. Yes. Thank you, Laurentio. Are there any questions or any more questions?
Yeah, thank you for these nice mini course. I have two questions. First, does your mixed host structure construction applies from the twisted Alexander module?
Possibly, but we certainly did not think about that, I have to say. So we're more concerned about relating it to this classical limit mixed structure, for example, on the generic fiber of the defining polynomial, of the defining map, and so on. There are various notions, there are various ways to generalize this Alexander module for, I said for maps from a quasi-projective manifold to C star, but you can take a quasi-projective, take an algebraic map to an affine torus, and now Moises and Eva are extending this to semi-abelian varieties and so on. So there are various generalizations in the multivariable direction, but twisting by representations, it sounds doable, so this is yet another line of things to do for the future, but yeah, thanks, this is a great question. We didn't do it yet, so it's very plausible, but we didn't do that yet. So I would assume in this case the representation has to carry some harsh theory in it, right? So it should be something like the representation doesn't come just a vector space with a homomorphism from the fundamental group to GL of that vector space. It should be more like maybe a variations of the fiber of, I mean, something that would give a variation of mixed structures, maybe an admissible one, or something with good, already good Hodge properties to be added on the top of the classical mixed Hodge theory that we have.
Okay, thanks. And the second one is, you mentioned the L2 Betti numbers, but there exists also a L2 Alexander polynomial. But maybe not theory people can correct me, but I think it detects the not. I mean, it's a very powerful invariant, but I don't think it's very easy to compute. Even for the, I think it's not computed for the entire Rolfen table of knots. So are you studying?
Right, so this I have to say, this is something that was not adapted to this setup yet because it's hard to compute. But there are, for example, even more simple-minded L2 type invariants like L2 signature, for example, right? That one can, in principle, adapt here from knot theory. And these are also, I mean, there are plenty of, the upshot here is that, at least from what I said, I'm trying to adapt to algebraic geometry things that people have done with great success in low-dimensional topology, right? And there are plenty of invariants that work in that setup that one would perhaps like at some point to have also in the algebraic geometry context. And so far, these are the things that you can see that in the second lecture I geared towards things I kind of relate to. And I'm sure there is much more out there, but this L2 polynomial, I'm not aware of anyone doing this in the case of plane curve complements.
Okay, because maybe it's easier to be compute for plane curves than knots, I don't know.
You may ask, is it log concave? Is it, yeah, all these kind of things, right? So we...
Okay, thank you.
Sure.
Any more questions?
So first of all, thanks for this nice course, and for me especially for the parts that are, I mean, I never work with this L2 and related things, and so just for the comment that you said that up to now you didn't find, I mean, Zariski pairs that didn't. So one of the points is all these invariants, okay, they are of course useful for Zariski pair, I would not complain of it, but they are useful for more things. Independently, they, okay, as you know, sometimes it's very difficult to extract, I mean, geometrical or topological properties from this kind of thing, and so you can obtain the presentation of the fundamental group, and then what? But having polynomials on this kind of structure is good. So for example, in particular, in the maximal cuspidal nodal curves that you talk about, most of them, they are, I mean, classical Alexander invariants do not give something interesting, but we know that the fundamental group is very rich. So I don't know if you computed things on this case. So
I computed very limited examples, so this is very good that you're mentioning this. I have to say I once visited Mutsuoka for like 2 weeks, and I sat down, locked down in an office trying to do calculations with gap and this kind of things. And we managed to check several other examples of Zariski pairs through these new invariants, but somehow we were not able to detect new ones. That's what I'm... so everything we kind of were computing, we're hoping, look, all these classical invariants for these potential candidates are the same, and we will be able to because he had some ideas of what would be,
Yeah.
like you say, you know, when the fundamental groups are reached and possibly they give
Yeah.
you examples of Zariski pairs, and at least I could not do it, but
Yeah.
as I said, this is still, to my mind, this is still an open problem for
Yeah.
all my students and everyone who
Yeah.
wants to contribute to
Mm.
this.
Yeah, and so in the same kind of ideas, for example, when Vincent and Jose Ignacio were with these twisted Alexander polynomials, I think one of the points, regardless again that they may apply to Zariski pairs, is the fact that even the appearance of nodes in the formation, so Alexander classical Zariski pairs is completely transparent for them, but it's true. And for example, also with Hero, we found some questions where the appearance of a node
Now
or
starts
like
contributing,
in
right?
the maximal ones is,
Right.
and it's nice to have some more concrete that it has a change of topology. So maybe these new invariants could.
So these are finite invariants and these are sensitive to nodes, right?
Okay,
Indeed, yeah. So
yeah.
these are already, yeah. So this
So
is
This is nice.
what we don't see with
Yeah.
with just untwisting or just classical Alexander polynomials. It's very possible that these new invariants detect. As I said, I mean, I'm sure people who are very good at computers can actually implement this in Czech. I'm not aware of, maybe Alex knows this, the other Alex in the back, if these things are implemented, some of these things like BNSR invariants are implemented in GAP or something like this. This would be a good thing to have in these computer packages and check at least, because by hand, I did calculations using Reidemeister Schreier, for example, to do presentations and so on, and that blows up quite quickly. By hand, you cannot. At some point, you have to stop.
But even so, it's good to have theoretical questions, because I mean, for example, if you try to compute all these kind of things like, I mean, characteristic varieties for curves, even you can plug in a computer. But for line arrangements, so you can compute the fundamental group, but you get so huge matrices that, so for example, in that case, without all these results about resonance varieties, you cannot hope to even compute, even you have. So it's also nice to combine not only computer help, but I mean, you need theory before also, as you.
I have to say, I hope that by the next Haka meeting, we'll have some joint work in this regard. So.
Thank you very much. A very nice course. I have a question. Maybe you can use the power structure that you define with the mixed Hodge modules apply to the links. No, because
Mixed Hodge structures for links. Did I understand this correctly? Ah, ooh. Oh yeah. Oh, this motivic. Right. So for the Alexander polynomial, I think this is isn't this what Anatoly and yeah. So we have a paper with Manuel Gonzalez, Anatoly, and myself, where we do motivic infinite cyclic covers, right? But I mean a little bit with some restrictions, and we recover at least the motivic Milnor fiber of the Nev-Losier and for rational functions and things like this. So yeah, you're right. Sorry, somehow my mind was so focused on curves, I completely forgot the motivic approach. But we do have something like this, and I'm told that more people are working in this direction nowadays. So Nikes told me that he had a student who did some calculations in this direction also. But yeah, this is. Of course, you can categorify all these invariants, right, at the motivic level. At least the Alexander type invariants at the motivic level. Thank you. Thanks for reminding me this. Yeah.
Any more questions? Any more comments? No. Well, thank you again.
All right. Thank you very much. This was a great honor to speak here, and I'm happy that you guys attended. So
we just have like 5 minutes, because even though you tried your best in the end, like questions. I just wanted to make so 2 announcements. One about the trip today. So after the mini course, right? After the coffee break, we'll have a short special session, and then the mini course after the hopefully we'll finish by 1:30. We'll try to. I'm just concerned that so in this trip we will go to the Pyrenees, and since it's like afternoon, evening, and it's like a 4-hour walk.
in the birthday of two friends. So I really have too many memories, and I could spend the whole lecture telling them. So I know both of them for a long time. So one of the first time that I met Alex was when I was defending my thesis at Complutense. At that time, it was so hard to use a foreign PhD title in Spain that you had to defend your thesis again. But we had to translate the thesis, and we learned that we had to translate the thesis 3 days before the deadline for handing in. So the singular group worked as a team, and we worked for 2 days and 2 nights translating, and Alex was all the time in the faculty, being so generous and helping me. I don't want to tell what the result was, so I forbid Complutense to publish my thesis online. And I also know Quique for a long time. So I was living in Madrid, not in Zaragoza, so our relation was many times in the phone, but I from time to time call him, ask questions of mathematics, and he's always giving answers, taking the telephone and helping. So the last time that he called me, I was in Budapest, and Enrique was with Alex in the office, and he called me to say, I have a counterexample to your conjecture. Which is something that is very common in our group. So it's really a pleasure to be a member of the singular group, which is the name that we have for the common project between Madrid, Zaragoza, and now Bilbao, and really is one of the best things that has happened to share my mathematical life with you. Is one of the best things that happened to me. So let's concentrate in mathematics. So the talk is motivated by Zariski multiplicity conjecture that says that if you have 2 hypersurface singularities, so you take a germ of hypersurface singularity and another germ, and you have a homeomorphism taking x to y, then the multiplicity of x at the origin must be the multiplicity of y at the origin. So this is of course a conjecture. Which is Zariski multiplicity conjecture, and there is a family version for this conjecture that says that if ft from Cn0 to C0 is a family with constant Milnor number, then the multiplicity of ft is also constant. So this is now a theorem. So this was known in for plane curves, and now is a theorem that I have proved together with Thomas Pelka. So this is called the family version of Zariski multiplicity conjecture because if the topological type is constant, then the Milnor number is constant. So this implies Zariski multiplicity conjecture when you can put the germs in a family. And to complete the status of the problem, at the end of, so the paper is available in the archive. And the end of the paper is an example. So some time ago, Enrique and co-authors, I don't remember who exactly, but you were in, and Alex. No, but it was not that example. So there is, now you tell me the authors. So there is one example of plane curve singularities with the same cipher form, but different embedded topological type. Yeah. Well, but you told me about this example. And now, if you take the double suspension of these two singularities, you obtain two topologically equivalent singularities, and a consequence of our theorem is that these two topologically equivalent singularities cannot be joined in a mu constant family. So our theorem also has as a corollary that the Zariski multiplicity conjecture not in family is strictly harder than the family version, and the status is open. So this ends the status of the problem, and now I would like to tell you a little bit what are the ideas to prove our theorem. So in the 40 minutes that I have is impossible to give a taste of a full taste of the proof, but I want to explain a little bit what are the main ingredients. So the origin of this way of thinking goes back to Acampo. So if you have a hypersurface singularity, in fact, you know that there are two ways of defining the vibration, and this is this will play a certain role in this talk. So one way of defining the Miller vibration is to take a very small ball, to take a disk, and now to restrict the function to the ball over the boundary of the disk, and this is a locally trivial vibration. This is the Miller vibration in the tube. And another way is to take the ball, to take off the link, to take the sphere, the boundary of the ball, you take off the link, and now you take f divided by modulus of f, and you send it to S1. This is the original Miller vibration. Both of them are topologically equivalent. And they give rise to a map. So there is a fiber, which is the Miller fiber, and you have a map that is the monodromy map. And Acampo was very busy studying the Lefschetz numbers of the monodromy. So he studied the Lefschetz numbers of the monodromy, the generating function, proved the Acampo formula in terms of the resolution, and a dream. And you not only study Lefschetz numbers of the monodromy, but you study Lefschetz numbers of iterates of the monodromy. So for each natural number, you get a Lefschetz numbers. And a dream would be that the multiplicity is the smallest number such that the Lefschetz number is different from 0. Well, this dream is not true, and this is the reason that Acampo methods didn't prove Zariski multiplicity conjecture at that moment. So as you know, computing Lefschetz numbers is studying the dynamic properties. Computing the Lefschetz numbers of iterates is studying the dynamic properties of the monodromy. So if the Lefschetz number is different from 0, then you know that there are fixed points, that necessarily any representative of the monodromy in the mapping class group needs to have fixed points. So in symplectic geometry, there is a famous conjecture by Arnold that is proved by now, that is states that if you have a Hamiltonian diffeomorphism in a compact symplectic manifold with some conditions that I am not going to explain, then the number of fixed points is at least the sum of the Betti numbers of the manifold. The left-hand number of such a map, because it is isotopic to the identity, would be the Euler characteristic. So the alternating number of the alternating sum of the Betti numbers. So the solution of Arnold conjecture motivated the creation of Floer theory, and this is the philosophy that underlies our proof. So what we are going to study is Floer symplectic representatives for the monodromy and Floer theory associated to them. And I completely lost track of time. So what time is it and how much time do I have? Because I want to control it from now. So when do I have to finish? I'll continue. Now you let me know. Only 25. Okay. So let's go straight to the point. How to define a symplectic representative of the monodromy and how to use it to try to prove equimultiplicity. So I will explain a geometric fact that comes from the proof of Le-Ramanujan theorem. Le-Ramanujan theorem is the theorem that tells that when the dimension is when you are not working with surfaces, mu constant implies topological triviality. And one of the steps of the proof is the following. So you picture the parameter space, and now you take a ball. You take a Milnor ball. You take a radius epsilon 0, which is a Milnor ball for the germ F0, and now you have the germ Ft, and you take the same size. You take the same size even if this size is not a size for the Milnor ball. So the Le-Ramanujan problem is hard because the Milnor radius may approach 0 as t approaches 0. But nevertheless, you take the same radius all the time, and now this defines the Milnor fibration for F0, and this fibration is equivalent to the Milnor fibration for S0. Oh, well, this should be pictured here. But it is not the Milnor fibration for the germ Ft. The Milnor fiber for the germ Ft is the part that is contained inside. So an important step in the proof of Le-Ramanujan theorem is to show that this covariance, which is Ft minus 1 of delta intersection with the ball, the Milnor ball for the for t equals 0, and now you subtract the Milnor ball for different from t, this is a homologically trivial covariance. Okay, so this is the only fact from topology of singularities that we need. And now let me explain how to prove the conjecture. So you consider the usual, so let lambda be the usual Liouville form in Cn. Omega is d lambda, is the standard symplectic form, and the standard symplectic form makes all the Milnor, all the fibers of the map symplectic manifolds. And now, what we would like is to have a representative of the monodromy that is a symplectomorphism. And I don't have time, so let me be sloppy. So I need formally speaking, I need an exact symplectomorphism. I will not say what is an exact symplectomorphism, but it's symplectic and a bit more. And this bit more is an interaction with the Liouville form. But we want a representative of the monodromy that is symplectic. And you know that symplectic maps preserve the volume. There is no guarantee that when I go around the origin and I follow a vector field, the volume of this fiber is going to be the volume of this fiber. So I cannot pass continuously by the fibers by preserving the volume. So it is hard to define symplectic monodromy associated to the Milnor fibration in the tube. And this is one of the problems that is addressed in our paper, and the solution is to change the shape of the ball. So instead of taking a ball, so we locate the intersection of the ball with the central fiber, and we create a kind of real hypersurface that doesn't have the shape of the ball, but this real hypersurface is what you use to bound the Milnor fibration. Okay, and now this sounds a bit like magic, but it is quite easy because you use the symplectic connection to create this hypersurface. So there is a God-given way of creating what we call the red balls. So first step, modify the shape of the Milnor ball. Second step, use Moser trick to create a symplectic monodromy. Okay, so now you have a Milnor fiber. Let me call F. And now I have a symplectic monodromy. I have the Milnor fiber 4,0, and I have the symplectic monodromy 5,0. So I want to make the picture a little bit different. You have F0, and I have 5,0. Okay, and I have also the symplectic form, or better, why not to be a bit more precise, the Liouville form. So I get a triple that is called by MacLean an abstract contact open book. So as I will explain in a moment, MacLean developments are completely essential to be able to get this proof. And I can do the same construction for t different from 0. But what is very important is that for t different from 0, we do not take, so we are not using the smaller radius, the radius that gives the Milnor fibration. So the fibration that we use that we associate for the general parameter is the red fibration that you are seeing in the picture. So we put the red balls in these two pieces and consider this fibration. So I get another abstract contact open book. So what abstract contact open book means a Liouville domain, which is the Milnor fiber, together with the Liouville form, an exact symplectomorphism it. And as you see, you can deform one abstract contact open book to the other. So these two abstract contact open book have the property of being isotopic. Okay, so now we need an invariant associated. So we have enhanced the Milnor fibration to the symplectic world. This is the upshot. And now we need an invariant that, and this Milnor fibration is inspired by the Milnor fibration in the tube. Now we need an invariant that, a Floer theoretic invariant. So there is, so it's a long tradition, but it started by Seidel and Uliarevic and MacLean. There are, and Salamon and Dostoglu I inverted the other. There are several authors that elaborated on Floer theory to be able to create a suitable fixed point Floer homology for abstract contact open books. So, but the thing is that if you have an abstract contact open book, which is, let's see, F0, 50, lambda 0, you can associate some invariant that is the Floer homology of 50. And now you put a plus. There are two versions, the plus and the minus, and we do use the plus. Okay, and now there is a theorem that says that isotopic abstract contact open book have the same fixed point Floer homology. So the theorem tells that the fixed point Floer homology for the monodromy for general parameter and for a special parameter is the same. And you can do this not only for the monodromy, but for all the iterates of the monodromy. For all M. This is isotopy invariance of Floer homology. Plus. All time plus in this. So in this talk I only be able to say the slogans of the proof, but no further detail. And okay, so now we know, and now I will state a theorem. Let's say theorem A, and this is proven in our paper. The multiplicity of Ft is the minimum of the M such that the Floer homology of Ft to the power M plus is different from 0. Okay, so the corollary of these two propositions or two theorems is that the multiplicity of F0 is the multiplicity of Ft. And now this, and now I have to explain a little bit how to prove theorem A. So now I have 15 minutes. So let me spend 5 minutes comparing with MacLean approach. So it is the moment of quoting MacLean and giving credit to him. So what MacLean did. So he did the same, he proved the same theorem, but for the Miller vibration in the sphere, which is not the same, or which may be the same, but is not proven to be the same, because the Miller vibration in the tube didn't exist before the symplectic Miller vibration in the tube didn't exist. But the theorem that he proved was the following. So you start by a holomorphic germ, and now you consider lambda a standard Liouville form, and now you consider the following pair. You consider the Miller sphere, and you consider the intersection of the Miller sphere with the zero set. Okay, you get the sphere and you get the link, and you get lambda restricted to it, and this is a pair of contact manifolds. So now let me the fact that this is a pair of contact manifolds is by Barchenko, and now theorem by Cauvel, Patrick Popescu, Pampu, and Nemeti associates well, it associates an open book. But the way that McLean proceeds is as follows. Use a construction of Giroux. And the construction of Giroux associates an abstract contact open book. Okay, so you get, and this abstract contact open book is from the Milnor fiber, the Milnor fiber in the ball with a associated Liouville form and a monodromy. So this uses some theorem of Giroux, and now McLean proved that the multiplicity M is the minimal. So he proved theorem A. Is true for this abstract contact open book. And now, what is the difference between McLean approach and our approach? And now it's easier to understand by looking at this picture. So for McLean, when t is different from 0, it is essential to work with the Milnor fibration in the smaller sphere. So it is known in higher dimension that this coverdisc is topologically trivial, but there is no clue that this coverdisc should be symplectically trivial. And this is the abstraction to apply a McLean approach in a direct way to get a proof of equimultiplicity of mu constant family. So somehow you should be forced to use the larger fibration that can be compared by isotopy in a direct way with the fibration in the of the special parameter. Okay, and there are other technical aspects that differ from McLean construction and ours. So the kind of invariance. So, but this is a bit technical, and let me skip for this talk. So this is not the only difference, but it is what can be said in the amount of time that I have. Okay, so now I have to give some clue on how to prove theorem A. Okay. So theorem A is proven in is the combination of two tools. So is monodromy with a special dynamics and McLean spectral sequence. So the combination of these two tools give rise to theorem A. So McLean was before us. So in fact, his paper was the sparking point that started our research. And in the course of his proof, McLean created a spectral sequence converging to Floer homology, and this spectral sequence is completely essential for the proof. So we have improved very slightly the spectral sequence to cover a little bit more general case, but really nothing. So at the level of a spectral sequence, everything is due to McLean. And we do have a different way of producing monodromy with a special dynamics. This is the main difference of our approach and his approach. Okay, so let me say what is monodromy with a special dynamics. So I have the Milnor fibration, and I have the symplectomorphism, and now I will state in a precise definition what is monodromy with a special dynamics. So we study the fixed points of phi, and we want them to be a disjoint union of sets bi, and bi is a codimension zero submanifold. So that is a domain that has the boundary is a codimension 1 manifold. So let's try to express this with a picture plus one extra condition, and the best is to picture for you, for those of you that have studied monodromies of plane curves. A monodromy of a plane curve could be something that preserves the composition that I have pictured, that well, let's take iterates, that some iterate is the identity here, and well, the monodromy could permute these two other components, but perhaps some iterate of it will leave these components fixed, and here the monodromy makes like a kind of dent twist. This is a situation that you are used to see. And this would be the manifolds, V1, well, let me call this V0, V1, and V2, okay? And special dynamics means that these are the only fixed points, but furthermore, there are small tubular neighborhoods. Small neighborhoods of these families of fixed points, and in those neighborhoods, so you have BI inside in a neighborhood NBI, and now the monodromy leaves NBI invariant and is Hamiltonian in it, is Hamiltonian on it. What means that it's Hamiltonian? It means that you have a function from this piece to the real. This function is constant in the shaded part, and it is not constant here because the monodromy is not the identity. Well, if it is not constant here, it may either increase or decrease as you leave the zero-dimensional family of critical points. And this allows to split the boundary of BI in two pieces. The boundary plus of BI and the boundary minus of BI. Okay? And there is a special place which is the boundary of the Milnor fiber, and now I have 50% chance to make it right. So there is a technical aspect in the definition of Floer homology, is that in order to define it, you have to destroy that the monodromy is the identity at the boundary. So in order to destroy it, you put a color and you make a Hamiltonian term. And this Hamiltonian term is, let's say, decreasing according to our convention. There is something in symplectic geometry that about 50% of the authors put the Hamiltonian vector field in one side of the symplectic form and the other put in the other side. So in our convention means decreasing. And this amounts, this will later amount to a boundary minus. But now I want to tell you what is the role of boundary plus and boundary minus. So MacLean spectral sequence tells that there is a spectral sequence converging to Floer homology such that the E1 page is made. So I want to converge to Floer homology of iterates of the monodromy. And now the E1 page have the following shape, are homology groups for certain case. I don't want to write the indexes of the BIs relative to the boundary minus of the BI. Okay, so this is a spectral sequence that exists whenever you have an abstract contact open book with a special dynamics. usual homology. Usual homology. Let me put a star. It can be any group. And now, how do you get a monodromy with a special dynamics? Okay, so let's. Now I have to stress that I will not use in any moment resolution in family. So I had to compare the Floer homologies of F0 and Ft. But I do the comparison without making any resolution. It is now that I make resolution, but individually. So let me pick a parameter T. Pick a parameter T. So everyone wants that I pick the T different from 0 because everyone wants to see how to use this non-trivial covariance. And now you do resolution of singularities. Usually you'd put the Milnor ball here, but the larger ball is cutting long. Okay, and now I don't have the time to explain what occupies 60% of our paper. But what occupies 60% of our paper is to be able to deform the monodromy to a monodromy with a special dynamics. Okay, so in order to be able to deform the monodromy with a monodromy of a special dynamics, we need, well, luckily you heard yesterday the talk of Pablo. So we use monodromy at radius 0, but not, we need to modify the Kato-Nakayama spaces, so the real-oriented blow-up, to a different space that topologically was created by Acampo back in the 70s. That is the Acampo space. It's a further blowing up that separates the corners. So we separate the corners, put some interpolating space, put a smooth structure in that space, put a symplectic form, and create something that is called the monodromy at radius 0. But the monodromy at radius 0 have wonderful properties that are the following. Now you can think of the usual description that you know for the monodromy. You split the resolution space in boxes and tubes. In the boxes, the monodromy is a kind of dent twist, and in the tubes, the Milnor fiber are a covering over the puncture exceptional divisors, and the monodromy is the covering transformation. So if you know the degree of the cover, you know if there will be fixed points or not. So you will have fixed points when the degree of the cover, so I have fixed points of the mth iterate of the monodromy if the degree, let me call mi, the degree of this cover if mi divides m, and otherwise this will not give rise to fixed points. So what Thomas and me prove is that there exists a representative of a symplectic representative of the monodromy that has a special dynamics, and the fixed points correspond to the tubes. For this, you need to take a resolution that is large enough because you don't want fixed points in the dent twist. And this condition is called M separating. So the resolution that you take is large enough. And roughly speaking is that if you have Mi here and you have Mj here, Mi plus Mj has to be larger than M. So you just do further blow up. So you do an M separating resolution, and now the fixed points of the monodromy of the mth iterate of the monodromy is a union, and now if you want, you call them BEI when Mi divides M. Okay, so let's see how many pieces of this I can get. I am going to do an Hironaka resolution. So means I only blow up. The first blowing up is going to be the blowing up at the origin, and I only blow up at singular centers. This means that the multiplicity of the divisors, so this Mi is the multiplicity of this divisor, the Mi are bigger or equal than the multiplicity, well, except this one. This one is the strict transform. So this M0 is equal to 1. So you have M0 is equal to 1. all the other MIs are bigger or equal than the multiplicity. And there exists a unique MI that is equal to the multiplicity. Okay? And now let's play with MacLean spectral sequence. There is something special. So there are two types of families. I'll finish in 2 minutes. There are two types of families of fixed points. Those that are associated to exceptional divisors and the one that is associated to the strict transform. So we prove that the boundary of V EI is always boundary plus. Okay? So this means that the contribution in the MacLean spectral sequence is the ordinary homology. But the boundary of the B is 0 is boundary plus of B is 0, disunion boundary minus of B is 0. And now I want to tell you what is boundary plus and boundary minus. This is boundary minus, and this is boundary plus. But this cobordism is homologically trivial. This is a consequence of Le Ramanujan paper. So, homology of B is 0, boundary minus of B is 0, is 0. So you don't see, using the homological triviality of the cobordism, you prove that you don't see this contribution in the MacLean spectral sequence. And now the proof is trivial. So if this contribution is not present, if you are below the multiplicity, there are no contributions. The MacLean spectral sequence is empty. And now you go to the multiplicity. There is only one contribution, and it is in a column of the spectral sequence. So the spectral sequence immediately degenerates. So the multiplicity is the minimal M, such that the Floer homology is different from 0. And, well, this is the idea of the proof. So I'll stop here.
Okay, thank you very much for the effort in being so quickly. So are there any questions?
Okay, so thanks, Javier. So it takes time to read your text because it's hard, but I think it's quite helpful to know where are the points. And so respecting to the non-family case, so probably not for the multiplicity conjecture, but even to see which are the different properties, maybe it would be nice to compute Floer homology in that case, not only look for the first one, but try to, and so I wonder if, there is any relation from the Floer homology of the of a singularity and the Floer homology of the suspensions in order to eventually start from the curve case where.
So, computing Floer homology beyond curves is very hard. So for curves, my students, Javi and Eduardo, proved that the MacLean spectral sequence degenerates. So so computing is easy. Beyond curves, the Floer differentials involve the solution of a partial differential equation. So it's not something that probably you want to do. But we have a conjecture that tells that the fixed point Floer homology of the mth iterate of the monodromy is the usual homology of the contact loci that you use to define motivic integration. And Eduardo, my student Eduardo, has already some experience trying to understand how this behaves under suspension, and it is not so easy. So the algebraic geometry counterpart of the conjecture in Floer homology shows that it might not be easy to a kind of Tom Sebastiani strategy.
Okay, but anyway, he's from Zaragoza, so I guess that he will be able to do it.
Any more questions?
For a mu constant family, do you expect all the invariants like the log canonical threshold to be
I think this
constant?
is proven. I think
proven?
this is known that it is. I think this is. I think so. Yeah.
Okay.
It works?
So you are referring to the Le-Ramanujan theorem, but there is an exception in that theorem. In the surface case, it's not valid. What
Yeah. What doesn't work in the surface case is the H-Coverdis theorem, but the
Yes.
step proving that the Coverdis is homologically trivial works in every dimension.
Okay, thank you.
So could you say something again about the examples of two topologically equivalent singularities that don't fit in a family?
I can say it again. So I cannot say the equations because they are long. But what you do is you take two plane curve singularities that have different embedded resolution, but they have the same cipher form. And now you suspend twice, so you add two disjoint variables square, and then you are in dimension 4. By results of Kerbein and Levin, well, the cipher form is still the same, and then by results of Kerbein and Levin, the embedded topological type is the same. Assume now that you can connect by a mu constant family. Since you took double suspension, the multiplicity is 2 in the two extremes of the family. But now our theorem proves that the multiplicity has to be constant. So the multiplicity of every member of the family has to be 2. And then you can play Moore's lemma in family, and you can remove one disjoint variable. And then you go back to a family of threefolds, you do the same trick, and you reach a contradiction.
Thank you.
Any more questions? No?
Very nice talk. Each time I understand better the proof, no? And now, can you give an idea how the spectral sequence of Malane is essential, or to one point you can extend this part to other problems in singularity theory?
To
other problems in singularity theory.
Okay, so it is tempting, for example, to try to treat non-isolated singularities. And for non-isolated singularities, even the symplectic monodromy in the tube needs to be defined. But I think it is possible, and not the MacLean spectral sequence, but the method that Thomas and me use, the Acampo space, we feel that can be used for other purposes, like finding Lagrangian tori in Milnor fibers, and so there are other problems that are motivated from symplectic geometry that we believe that the technique will help.
Okay, thank you very much. So maybe we thank the speaker again. So we come back at 12:15.
Okay, so before we begin the, oh wait, better not. So, before we begin the last part of the morning with the mini course, and knowing that today's schedule seems to be thrown off completely of the time. So I had asked 3 of the members of the scientific committee that have been very committed. I really want to thank them for their support, to prepare something like an overview of Enrique and Alejandro's work, so that we all have even though we've been having an idea of what their main results have been, or their main focus of work. So I think they will see it in a comprehensive presentation here. So we'll first have Professor Anatoly Lipgover from University of Illinois in Chicago, and then I don't want to be introducing them every time, so that we make it a little bit more continuous. So after that, we'll have Professor Alexander Suciu from Northeastern University, and then Professor Ignacio Luengo from University Complutense de Madrid, and they will give us this comprehensive timeline of their scientific work. Thank you.
Did you want to use this? Yes. Right. Okay, just in case. So how do I turn
Or it's on.
It's on. Okay, perfect. Okay, well, thank you. Okay, I was asked to talk about, say a few words about Enrique. So, well, what's the best way to say about mathematician, talk about their work? Well, but before I'll start to talk about Enrique, let me say that Alex, well, always was admiring your work and looking forward as much as possible to see will come out more of your work. well, okay, I'll start with the sort of formal thing, stats. If you look in math review, so Enrique, it credits him with 87 publication and growing, and 700 citation and growing also. So if you look in math genealogy, so there's 4 students, 4 descendants. Well, it doesn't mention how many people owe to his to his teaching of all of us. So and ancestry goes back so with his PhD advisor Claude Weber in Geneva, and back through Erisman and to Elie Cartan and Hefliger to Elie Cartan and Lefschetz. So the work of Kike is devoted to singularity theory, affine algebraic geometry, and topology algebraic variety in broad sense. So I enlist some topics, and I hope it makes justice. So the topology of the complements to plane curve, complements to arrangements of lines, Alexander type invariants of quasi-projective varieties. Now Hodge structures associated with non-traditional, but Warkike showed very important class singularity, like super isolated, quasi-ordinary, etc. Then another topic is zeta functions of singularities, P functions, and monodromic conjectures, and topology of families of polynomial related to Jacobian conjectures. So each of these topics has, so it's fairly different lines, but interrelated, and it's cover a lot of ground. So there's no way I can say it in a few minutes, about all them. So I talk about the first one, topology of the complements to plane curves. So so this is probably the most, well, it is the most quoted, most noted paper by Enrique, which is very shortly after his getting his PhD. So that's where this term Zariski pairs was inaugurated, and it's catch up, and now most of us use it here. So perhaps they should be called Zariski-Artal pairs. So, so Zariski pairs, it's a somewhat loose expression, so which curves, pairs of curves with the same invariants, but non-equivalent. And what invariant it means in each particular instance may vary. It could be combinatorial, the same Alexander polynomial, the same invariant, the same profile completion, etc. It could be different ways, different invariants. And equivalent also could be have different meaning. It could be deformation equivalent. You can pass from one curve to another via equisingular deformation, or it could be diffeomorphism or homeomorphism of pairs, plane and together curves. So this is somewhat loose sense. This word, but so it's very useful, very efficient. So there is good reason why this paper so much quoted and was so influential. Well, so I just mentioned several things which are there. So there's this lovely thing, this abelian covering trick. So that's covering of projective plane via abelian cover, and that allows construction curves, very efficient construction of singular curve with complicated singularities. Like for example, if you take, so this abelian cover has 3 ramification lines. So if you take pre-image of the curve which has, for which this line is inflection, so you get curved cusps when you lift it. So it's very beautiful construction, very simple and very efficient. So as a result, in this paper, so Enrique constructed Zariski multiplots. So there's, of course, with higher singularity is A5 and A17. So maybe one should put in perspective. So how important advance was that at the moment? So at the moment there was known only one Zariski pair, which the one was found by Zariski, that he constructed two curves of degree 6 with 6 cusps, and which were not deformation equivalent. And he showed that, in fact, they have different fundamental groups of the complements. Now it's also very interesting methods which Kike used in this paper. So he used the homology of the he used essentially homology of the Milnor fiber. Essentially homology of the Milnor fiber. So, and that was, he made a very detailed, interesting calculation. It was, but it follows path of the work of Elena Hinault, who wrote about 10 years before that. So she actually noticed that the cyclic covering trick, which she used in the proof of Kawamata-Vivek's theorem, can be used to make calculations of homology of the cyclic cover, maximal cyclic cover, branched or unbranched. And that sort of fits in the scheme of the Zariski, because most interesting, most invariant which he used, Zariski used, it's homology of a tower of a covering, of this full tower of the covering. So he showed that the Zariski was showing that it's Betti numbers in tower of the covering, cyclic coverings, it's periodic. And so that's actually invariant which distinguish curves. So in fact, Zariski also showed it's enough to take maximal cover. So that's why calculation of Hinault and Enrique were relevant here. And so Hinault just made one calculation for this Zariski case, but what's sort of important in this work, so it's greatly expanded. Scope of examples which became available for calculation by this method. So, well, that sort of close, that's what created my connection with Enrique, which has continued since then. So that Alexander invariants, so they invariant fundamental group, as we heard in Lorenzo talk. And so what is also important, they control homology of the cyclic cover, of this tower. So that's actually historically quite remarkable. So Zariski used this tower, but somehow he didn't manage, he didn't connect with Alexander polynomial, but he has something very close. Anyway, so that I was studying also about 10 years ago, 10 years before this paper, this Alexander invariance in covering, so that's created our connection, well, thanks to Pierrette, where we met in Bordeaux with Kike, and Kike got very much involved in study of Alexander polynomials after that. So here's, I just quote one of the papers which deals with that, but there are many, many more. So that's also, so it shows that sort of Zariski pairs exist in different sense than Zariski used it. So that it shows that Alexander polynomials do not separate equisingular connected components of curves of the same degree. Well, so there are many, one can talk very long time about Kike works, and since I try to be brief, so I will mention just two beautiful ideas which I trace back to Kike. So that so one is just this initiation of the study of Zariski pairs formed by Galois conjugate curves. So, and of course there is some sort of reasons why one look at that, but So this is very nice paper which just convincingly shows existence of this phenomenon and how important that, and the work of that continues by Kike students. Well, Benoit has works about arithmetic Zariski pairs, and so there's very interesting line of research. So that another beautiful idea, which comes from Kiki work, is the relation between roots Alexander polynomials and orbifold groups. And so basically, if you have a map of the complement on the orbifold, and the orbifold has orbifold fundamental group has non-trivial, Alexander polynomial has non-trivial roots, you can pull it back and you get a non-trivial Alexander polynomial with the same root upstairs. So that's sort of just gives a very interesting geometric meaning for the roots of Alexander polynomial. So, and so this topic also was developed so with our paper with Jose Ignacio Cogayuda. Just a second. Yeah, I'm sorry. Well, so the paper in terms of singularity, that's was with Enrique, so that's where our collaboration. And and also John with yeah, okay. Maybe this is yes. The microphone. Oh, okay. Oh, I'm sorry. That's right. Thank you. Thank you. Yeah, and so both of these papers together with Enrique. Okay, so this is also important idea. So just it leads to connection between Alexander polynomial and some Diophantine equation over function fields. So that's sort of related to what Lorenzo was talking this morning about bounds and degrees of roots of Alexander polynomial. Okay, so as I said, so there's I can talk a very long time, but I'll stop here. I want to wish you happy birthday and a lot of successful, very interesting work. Continue the space. Oh, I'm sorry. I forgot fun part. So that's, I think it's an Oberwolfer, and so this is Mike Falcon, he's not here. And finally, happy birthday to you both, guys.
Okay, but now what do I do? Okay. I'm very honored to give this short presentation in honor of Enrique and Alejandro, but mostly I concentrate here on the work of Enrique. And let's see, okay. So you heard from Anatoly a lot, so let's see if I can add a little bit. So his work, Enrique's work spans more than 3 decades. And as you heard, it covers an extremely wide range of subjects, ranging from algebraic geometry, algebraic topology, commutative algebra, group theory, Haploid arrangements, singularity theory, complex variables. It's hard to count, but I think it's about 90 papers. And what's also remarkable, and I'll try to emphasize this, the range of how many collaborators. You know, I counted 32, but probably it's even more if you add also the papers on the archive. Okay. So what I'll try to do now briefly is to group this, work. I cannot write all 90 papers, and you heard some of them from Anatoly, somehow by subject, although they, interact and overlap. And so let me start with Hyperton arrangements, because I know more. And part of this is kind of a historical perspective. I said, if you look at Massanet, the first paper appeared in 91, but the one that actually, when I first heard about Enriquez work was this preprint from 1990, sur le premier nombre de Betty de la Fribourg 2009. And I was just starting and kind of, with Dan Cohen, trying to figure out how to do this type of computations. We had no idea, and then we're looking for some examples and found this, and then, he computed the first Betty number of the Milnor fiber of the Breda arrangement, and it was 7. And we did the computation by totally different methods, and they were very excited. We got the same answer. I said, okay, we're on the right track. So that was an influential paper, at least for me, okay? And I think most of it appeared in the second paper, and you can see then there was all this work on like the Rybnikov arrangements and various topological invariants of line arrangements. For example, starting with work with Jose and Jorge and Marco, and then also more recently also Benoit and Vincent. Okay, so that's one topic. The other one, very much related in the spirit of how to understand the monomial of the Milnor vibration. It involves this cohomology jump loss sign, more specifically the characteristic varieties, and also the braid monotomy. So there was this very well-known paper in Duke from with Jorge and Jose, and the second paper also, it's a very interesting paper that I liked, and well, all of them, but I think probably the one that influenced me personally the most was this one, the characteristic varieties of quasi-projective manifolds and orbifolds, with Jose and Dan Mattei. That has a very beautiful interplay between the geometry and topology of this jump loci and the depth and so on. It's a very influential paper, and also this one with Anatoly that you heard about, I think. Okay, anyhow, so that's another subject. And then you heard quite a bit about these Zariski pairs. This has been one of the mainstays of Enriquez's works through the years. From this first paper that selected by the Zariski, and going through various other kind of connection with Mordell theory, with and this kind of arithmetic kind of considerations, and again, look at the range of co-authors. He goes also now with Hiro Tokunaga, and I think the other ones I mentioned before. Now, singularity theory, this is kind of everything kind of revolves around singularity theory, but this doesn't fit in the other branches, okay? So I put them on this slide. But mainly is zeta functions on monodromy, the monodromy conjecture, and some other consideration about Milnor numbers and singularities. Some work now you see also with Pierrette Casson-Nogues. I'm trying to kind of also mention some of the people here that also came to the conference and highlight their joint work. Well, Alex Dimka couldn't come here, and also Javier Fernandez de Popadilla and Alejandro Mele. Okay, so you can see here another kind of depth to Enriquez's work and how it reaches to so many other branches of mathematics. And finally, last but not least, connections to group theory. So, there's a study of acting groups and Bézier-Nabridi groups, things to do with log central series, and this very interesting paper about torsion the log central series quotients that disprove a conjecture that I made some years ago. And anyhow, and you see now here another list of co-authors, Jose and Danny, and but also Benoit and Juan, and Santiago, right? This is a very recent paper. So you see pretty much I exhausted almost all of mathematics, nothing about probability theory. maybe from 10 years from now. Okay, so that's all I had to say. Happy birthday.
Okay, do you hear me? No? So I have to talk 5 minutes about Alejandro, So what can I say in 5 minutes? So first, let me say that this conference was planned at the beginning as a commemorate Enrique. But in Madrid, we at the moment think that maybe it's also a good occasion to celebrate Alejandro. So I would like to thank Enrique for sharing this merited celebration with Alejandro. And also, of course, Jose Ignacio, who organized everything. So we'll start. First, I knew Alejandro since 32 years ago. He came one day to my office to asking to some work for the thesis. I must say that I didn't teach him, so probably because of that, he didn't come to ask a thesis to me. Okay, then I really I wanted to say first really something about Alejandro's character. Really, he is a wonderful person, a wonderful friend, hardworking, and about all also is very easygoing. So I never get, no one found never Alejandro upset, but really is easygoing up to a level completely incredible. So he's really a good friend. I also wanted to say that myself, I also easygoing, but another level, a lower level, no? But, but really, in 45 years in the university, I never get upset. Only my sons has the ability to get me upset. But this is normal. Okay, so, and all this year has been great with Alejandro, but also, I mean, having his friendship, and also I wanted to mention, of course, Julia. No? We've been together in many places, and we enjoyed all this time. And so, and I also wanted to thank Julia and his 3 daughters that they are here, I guess, around, for all the time that we pass together. Okay, then I will just say a few words about Alejandro's work. Let's see. Okay, so using the same layout of Anatoly. So he has more 55 publications in Mathnet, more than 470 citation, and for the genealogy, I mean, they have 3 descendants, 3 students, PhD students, and then for the genealogy, it goes to Germany, von Staudt, and of course, as many of us, to Gauss. But I will, if I can just resume in a phrase, the work of Alejandro is every kind of invariant coming from the resolution. So in this sense, in spirit, the grandfather of Alejandro is Zariski, but it do not appear here. Okay, so here you see Alejandro has 17 collaborators. I am the most honored. I mean, I was really very lucky to find Alejandro. We collaborate in 45 papers. Also Sabir, 22. I forget Enrique. Enrique is... Enrique has 20 papers. But the way in Madrid we have a different notation. So we say Enrique and Alejandro instead of Kike and Alex. So I follow Madrid notation. Okay, so Enrique, Pierret, and many others, Javier, Andras, Terry Walsh, Cogolludo, and many others. And also, let me mention that he has really only 3 papers alone. They are probably the one coming from the thesis, no? I mean, or they, not from the thesis, but ideas that come from the thesis. So let me just mention, this is the last slide, so don't worry. So we can really talk a lot about Alejandro, but they did not give me time. So Alejandro's work is devoted to singularity theory in a broad idea. Then I find algebraic geometry, and as I say, every kind of invariance, arithmetic, motivic, topological, geometric, coming for resolution of singularities. Okay, so this is a good, and for more, on the topics that were there, as I say, partial resolution of singularities is something that comes from his thesis and has a very interesting paper. Then power structure, it was mentioned by Sabir Ayer that gives some details. In fact, the paper on the power status is has more citation. It's like 50 citation. That's because this construction is very, it can, as I say, it can be used to reprove some results, but also to get many new results. And that many people, physicists, people working in mirror symmetry, etc., use this as a tool. So really, and of course, the ideas of Alejandro are there in a deep way. So we are also, and the rest is probably you also see in Anatoly's slide, because the rest is also joint work with Enrique. So we work the monodromy conjecture. You have 2 or 3 papers. I think the second most cited is one of the monodromy conjecture for super isolated. Also zeta function of singularities and B function and topology of families of polynomials connected to the Jacobian conjecture. And as I say, there is really a lot of work of Alejandro here. I'm sorry I cannot give more details, and also I cannot mention more collaborators, but maybe I will share some pictures. So let's see. Okay, so this is one picture. Did you know where is this taken, Alejandro? Can you guess? Anyone can guess? I will say you. No, it's here. So now you see. This is Oaxaca. You see the front there, so this is in Oaxaca. Okay, so there is other collaborators. Here is with Sabir or Musu Oka, and this is Terry's house in Liverpool. Okay, and there's another. Here is other collaborators, but not Alejandro. And here there are many more collaborators, but also is Alejandro, but it's difficult to see. So in 10 seconds you can ask, where is Alejandro? But you say that Pierrette, Felix, many others. So this, I'm sorry that I have been so time, but again, I'm really, I'm very glad to have the opportunity to say something about Alejandro, that has been a good friend, and also very important in our main work. I hope that we will continue to work, and I become emeritus professor this month of August. So I hope that I will convince Alejandro, Pierrette, Enrique to work, for instance, in the monodromy conjecture. It's something that we have when we have time. Now Pierrette and I are retired, so I hope we will continue to work on that. So thank you very much.
So you've seen pictures usually in the you've seen pictures in the university, what is it? Or is this French? Okay. So this one? No, I don't know why. Wow. Yeah, I don't know what's happening. Does anyone know French? How do I? Well, I don't know. Maybe I'll just show it like this, but how does this? Jorge, do you know how to change this? Pantalla completa.
Si no lo puedes pasar.
No, para que no enseñe las notas.
¿Y por qué no lo pasas?
Bueno,
¿Lo pasas a PDF?
ya, pero tenía el paso de una a la otra automático.
Ah.
Okay, so maybe just this. So we've seen more or less canonical pictures of them, and hopefully we'll show some a little bit special pictures. Working hard as always. Okay, so that's. All right, so.
Okay, thank you. Yeah, thank you.
All right, so it's my pleasure to introduce the next speaker, Masahiko Yoshinaga from Osaka University, who is going to start a mini course on topological and enumerative problems of hyperplanar arrangements. Okay, so Masahiko.
Yeah, thank you. Thank you very much. Okay, so first of all, I'd like to thank organizers for inviting me this great opportunity, great conference, especially giving a chance to give a course, mini course in front of two great mathematicians, Enrique and Alejandro, and also great audience gathering for two mathematicians. Unfortunately, I don't remember precisely when and how I met with Enrique, but probably it was in 2003. So at that time I was a PhD student in Kyoto, but there was a very big conference on singularity theory at Sapporo, organized, maybe Professor Tokunaga and Shimada coming here are part of organizers. And at that time, so this is clearly my first encounter with mathematics of Zaragoza. I mean, Jose Ignacio gave a very nice talk on the Rivnikov examples, and it was really striking experience for me. And after that, I feel, yeah, every time I wanted to understand mathematics from Zaragoza, and it is, yeah, one of major parts of my research activities. Okay, so in this talk, sorry, one more point. So after that, I'm very luckily have a chance to stay Zaragoza with my family. So for 2 months in 2012. So it was really special occasion for my family too, because my daughter became 1 year old in Zaragoza and stood up first time in Zaragoza and started to work in Zaragoza. Yeah, anyway, it's really special time. And also, I discussed many mathematics with Enrique, and it's really inspired from him. Okay, let's, so this is rough plan of my talk. There are mainly 3 parts. So first part is some introductory part. And the second part, I'm talking about topological problems, and mainly on Milnor fibers. And in the third part, I'd like to talk something about geometric structure behind enumerative polynomials or quasi-polynomials. Yes, so let's start with the introductory part. So here, let V be a L-dimensional affine space over some field K. So in this talk, hyperplane arrangement means just a finitely many collection of affine hyperplanes like this. And we denote by M the complement of hyperplanes. And now I'm introducing the notion of characteristic polynomial, which is the, as far, in my opinion, the most important invariant of the hyperplane arrangements. And also, I'd like to emphasize this measures a kind of size of the complement. In the I'm talking in detail later. Anyway, so let's start with very elementary things. So everyone knows if you have a finite set A1 and A2 in a finite set X, then you can compute the cardinality of the complement like this. So the cardinality of the complement of union A1 and A2 is computed as the cardinality of X minus that of A1 minus A2. Then we have to compensate something. Similarly, for any number of finite sets, we have this kind of formula. It is sometimes called inclusion-exclusion principle or something like that. So here, this bracket n means just the finite set from 1 to n, and A sub I, this appears frequently in my talk, but A subset I becomes the intersection of these objects. And we also, this is so conventionally, A sub finite set here always means the total set, total space. Then we can define the characteristic polynomials similar way. So let A be an arrangement as in the previous slide. Then the characteristic polynomial of A is the sum of some monomial t to power something, where I runs all subsets such that the intersection of hyperplanes is not empty. So minus I to the cardinality I times t to dimension of the subspace H sub I. So this means the intersection of all hyperplanes. So So for example, for this case, the characteristic polynomial can be easily computed like t square minus. Okay, so we have to consider all subset of 1, 2, 3. So there are totally 8 subsets, including empty set. But among them, the 1, 2, 3 does not have intersection. The intersection of H1, H2, H3 becomes empty set. So we have sum up 7 terms like this, and we get t square minus 3t plus 3 is the characteristic polynomial. And so we can easily, very elementary way, easily prove that for line arrangement, the characteristic polynomial is nothing but t square minus the number of line times t plus some constant term. So where constant term is the sum of cardinality of a p minus 1, where p runs all intersections like this. And a sub p means the, sorry, I don't, here. So a sub p means the set of all hyperplanes containing p. So we can compute the characteristic polynomial of line arrangements very easily. So now I'm talking about some basic properties of the characteristic polynomial. So I'm especially I'm describing the inductive, recursive behavior of the characteristic polynomial in the following way. So starting from arrangement A, we fix one of hyperplane, say the final nth one, Hn. Then if we remove Hn, we have some smaller hyperplane arrangement. We call this A prime. On the other hand, here Hn is a one-dimensional lower affine space. So we have a natural arrangement structure, hyperplane arrangement structure on Hn. So this we call A double prime or A second. So it is very easily observed, but that we can compare the complements of these three arrangements. So complements, I mean removing all hyperplanes from the total space. Then the complement of this A prime is disjoint union of that of A and that of A second. So it is just because this part is missing here, but it is here. So the complement of A prime is equal to the disjoint union of two other complements. So this observation leads the following, the so-called result, so-called deletion restriction formula. The characteristic polynomial can be characterized by the following recursive relation. So if A is empty set, then the characteristic polynomial should be T to the dimension V, total space. If it is not empty, then we should choose one of hyperplane Hn, say Hn, then construct A prime and A second in the previous way. Then the characteristic polynomial of A is equal to the, that of A prime minus that of A second. So from this formula, at the level of Grothendieck ring of varieties, the characteristic polynomial is nothing but the polynomial which expresses the complement in terms of affine lines. So this also easily proven from this formula. So yeah, now let's go to some famous, well-known results on the characteristic polynomial. The first one is now from our definitions, it's very easy to prove, but usually go back to Claypo and Rota. So if that defining field is a finite field FQ, then the cardinality of the complement, so it is just a subset of FQ to dimension L, so it consists of just finite points, is exactly equal to the characteristic polynomial of Q. And the second formula is also easily proven by using this recursive relation, but if that arrangement is defined over a real number field, then and also we need some assumption on the essentiality. So this means that hyperplane arrangement should have a zero-dimensional intersection. So so it is not very important, but so anyway we have to assume this. Then the number of chambers or number of bounded chambers can be computed by the as the special value of the characteristic polynomial, say at -1 and +1. So for example, if this arrangement consists of 5 lines, the characteristic polynomial is t squared minus 5t plus 6, then the value of -1 is equal to 12, value at 1 is 2, and 2 expresses this, there are 2 bounded chambers here, and 12 you can easily count all, there are 12 chambers altogether. And also, if that arrangement is defined over complex number field, then the complement is now connected affine variety. So we can consider the Poincare polynomial of this space, but it is also computed from the characteristic polynomial by minus t to L times this something. So for this example, it becomes 1 plus 5t plus 6t squared. So the coefficients of characteristic polynomial is essentially equal to the Betti numbers of the complement of the complex arrangements. And one more very recent, more famous result is so there are some non-trivial inequalities among coefficients of the characteristic polynomials. So it is, I think, the first publication of Junha in 2012. So the characteristic polynomial, the coefficients of characteristic polynomial is alternating actually. So this is well known and easily proven by using recursive formula. Then, so these A1, A2, AL are non-negative integers, and among these sequence, AI square is greater or equal to AI minus 1 times AI plus 1. So this is the so-called log concave inequality, and I'd like to survey the proof on this later. Okay, so now to Tensor. So there is one of the most important example. At least personally, I like this example very much. So there is the so-called braid arrangement. Here, blue of L is the set of hyperplanes Hij. So Ij runs from these regions, where Hij is nothing but Hij is defined by the it is the hyperplane in KL, where i's and j's coordinates are equal. So xi minus xj equal to 0 is the defining equation of this Hij. So here I don't give precise field, but so if we consider finite field if we consider this arrangement on finite field, then the complement is, as I said, finite set. But the cardinality and the cardinality of this space is very easily computed. Actually, it is, I think, very elementary enumerative combinatorial problem. So actually, if we consider what is the number of points in this space, so this is, I have to count the tuple of x1 to xl satisfying certain properties, but the properties is nothing but xi should be different from xj. So this means x1 to xl are the sequence of in Fq which is mutually distinct. So we can count as follows. So x1 has q possibilities. Then the second one, x2 has q minus 1 possibilities because we had already chosen x1. So x2 should have chosen from other q minus 1 options. Blah, blah, blah. Then q times q minus 1 times q minus l plus 1. So this is the cardinality of this space. And as I said, this is nothing but the characteristic polynomial of Q. So if we consider this arrangement in over real numbers, then there is chambers, and so it is well-known fact, but the chambers are encoded by permutations. So actually, so the symmetric group acts on the set of chambers transitively, simply transitively. So the number of chambers is equal to L factorial. And also it is the it is nothing but the characteristic polynomial of minus 1. And if we consider this space on complex number field, then this space is sometimes called the configuration space on the plane, complex plane. And between such configuration spaces, there is a natural fibration from L points configuration space to L minus 1 points configuration space, just by forgetting final points. So x1 to xl is mapped to x1 to xl minus 1. And this fibration, so this is a fibration with fiber x1. So the fiber of this point is nothing but the choice of xl, which is from c minus x1 to xl minus 1, because xl should be different from other l minus 1 points. So using this fibration is not a trivial fibration, but luckily it is the situation that we can use Rayleigh-Hirsch theorem. So we can compute the Poincare polynomial like this, and also it is also equivalent to the characteristic polynomial. Okay. So now I'm going to talk about the characteristic polynomials are related to many other enumerative problems, but here just one of them, the so-called the counting graph coloring, or sometimes so it is called chromatic polynomial. So here let G be a graph, finite simple graph with vertices 1 to L. So we consider this kind of objects. So these are objects we are considering now. Then the map, so we are considering coloring on the vertices. So it is a map from the set of vertices to some finite set. So here K means the number of colors. So the map C is called a K coloring if it satisfies this condition. So this means so two adjacent vertices should be attached different colors. Then we can count. So clearly, so this is the finite. So the set of all colorings, K colorings, is clearly finite set, and we count this finite set, we call this cardinality chi of gk. So this notation may be confusing with compared with characteristic polynomial, but it is soon justified. So very baby example, easy examples are, so if we consider this two vertices graph, then the coloring is clearly k colorings and k minus 1 colorings. So here, like this. So, and one of the most important idea to compute this chi of gk is the following deletion contraction formula. So if we fix one of edge E of G, then we can construct two other graphs, say, just removing E from G, we have this graph. And also, we can contract, we can collapse the edge E, then we have this graph. So here, there are two vertices, two edges containing, connecting here, and so in this talk, we consider only simple graphs. So we just identify these two edges when contraction. So then, if we consider the coloring of this central one, the removal one, then the so we call vertices here V1 and V2. Then the K coloring of this removal G minus, so deletion G minus E is either, so every coloring is either V1 and V2 have the same color or different colors. And these are corresponding to that of coloring of G and that of coloring of G over E, the contraction. So because if we have edge here, so V1 and V2 should have, V1 and V2 have the same color, then it is equivalent to considering the coloring of this contraction. So from this observation, we have the following behavior of this cardinality of K colorings. So so this is the number of cardinality of K colorings. So if the set of edges is empty, then clearly so we don't have any restriction on the coloring. So it has K to L, so the number of vertices colorings. But if edge is not empty, then we can we can do this procedure. Then the coloring of, so the coloring of this one is this one minus this one. So we have this formula. And these formula, so this is purely graph theoretic enumerative problems. But this looks very much like the that of characteristic polynomial, the behavior of characteristic polynomial. And it is actually true in the sense that we can construct a hyperplane arrangement from a graph G, say A sub G, to be the set of Hij. So Hij is that appear in the braid arrangement. So collecting Hij for each Hij, then we have some hyperplane arrangement. And actually, that characteristic polynomial of this arrangement is exactly equal to the of K is exactly equal to this chromatic polynomial. So now cohomology ring. So so I'm how to, okay, yeah. So maybe I continue. So now I'm going to talk about the very famous presentation of the cohomology ring of the complement of hyperplane arrangement. So first of all, I think one of the most simple hyperplane arrangements complement is this algebraic torus, because C cross to N is can be considered as a complement of coordinate hyperplanes. It is also sometimes called the Boolean arrangement, but anyway, so this is the complement of coordinates hyperplane arrangements. And it is well known that the cohomology ring of this space, and this is also homotopy equivalent to the N torus, compact N torus. And the cohomology ring is isomorphic to the exterior product of this free abelian group. So this is classically well-known fact. And for hyperplane arrangement A, we can fix the defining equation alpha I. So HI is a hyperplane. So it is defined by some linear equation equal to 0. Then using these linear polynomials alpha 1 to alpha n, we have a fine linear map from CL to Cn. And our hyperplane arrangement is living in this CL, and the complement is nothing. Complement is an open subset of CL defined by alpha 1 is not equal to 0, and alpha 2 is not equal to 0, blah blah blah. Alpha n is not equal to 0. So this is an open subset. We have a fine linear map. So here Cn has this algebraic torus as open set. And this space is nothing but the pullback of this, the inverse image of this open subset by this affine linear map. So we have a map from complement to this affine algebraic torus, taking a cohomology ring. Cohomology ring is a contravariant functor. So we have an algebra homomorphism from cohomology ring of this algebraic torus to that of the complement of arrangement. So this is actually surjective, and we have so the Auric Solomon gives a presentation of this algebra as the quotient of this exterior algebra as follows. So Auric and Solomon defines an ideal of this exterior algebra as follows. So this ideal is generated by two types of elements. So first type is E sub S. So where E sub S means so the exterior product of these generators for subset S of indices N with which has empty intersection. For example, if we have two parallel hyperplanes, then the intersection is empty. So then in that case, the product of corresponding hyperplanes becomes should be 0 in the cohomology ring. So we include this product in the ideal. And the other one is a bit non-trivial, but if we have a subset S, so called dependent subset, but subset of indices S such that the codimension of intersection is less than the cardinality of S. So it is, in other words, so this is not the how to say normal crossing intersection. Then we so we consider this element. So I don't explain how this appears. How this appears, but so this is sometimes called Arnold relation. But anyway, the ideal generated by these two elements gives a precise presentation of the cohomology ring. So it is so-called Auric-Solomon algebra, and EI in this presentation is is corresponding to this log form in the cohomology ring. first cohomology link. Yes, so this is just one example, and so in this example we have such presentation, and so cohomology ring is a graded ring. So if we and graded commutative ring. So and sometimes it is denoted by a sub r upper dot. So r is the coefficient ring. And if we fix the degree 1 element, then the multiplication gives a cochain complex, because so this is odd degree homogeneous element. So omega times omega is always 0. So this multiplication by omega gives a cochain complex, which is called Aomoto complex. So which plays very important role in later. Okay, yeah, it's very good point to stop today. Thank you very much.
All right.
Yeah.
Yeah, maybe somebody else? No? No? Yeah, okay.
So yes, thank you very much. So I hope that since you are very pointed to the starting from topology, but from you did here, so there are also, so it's very nice that you put, so a lot of properties depend on the field where you define the question. So, and so I hope that, so maybe tomorrow you will speak about the relationship with the chambers and cohomology and homology.
Yeah. Okay. Yeah. Thank you. Yeah, I will.
Maybe a comment. So maybe this is what you meant. I mean, this Aomoto complex depends on the characteristic, right? Or at least the cohomology of this Aomoto complex.
So sorry.
The cohomology of this complex, of this Aomoto complex, depends on the characteristic of the field.
Characteristic of the field. Yeah. You are right.
Are you gonna tell us more about this tomorrow?
Yeah, I will. Yeah, I will talk. I will talk on your result. So there, I will definitely say something.
Okay. All right. Maybe so. Maybe we stop. Or okay. So let's thank Masahiko again.
Yes. I also want to thank him because he has been so flexible so that we can make it work. So remember, if you need to change or whatever, by 2, we should be there. Like, I would like to leave by 2. So that means at the residence, and then we get on the bus, right? And the picnic will be there. The picnic will be on the bus. Yeah, remember, temperatures will drop up on the mountain, so bring